And I want to talk about a few points or actually one point that I noticed when I sort of teach climate change at the university, that the students all are very well aware of global warming and think they know it all. And then actually what it comes down to is that actually my wife and I, we both teach, we notice that there's a real problem, or that there is a lack of awareness what's the difference between radiation and heat, so of these different forms of energy. And I think that actually has some broader implications in terms of how we analyze climate data, and because it also actually shapes climate patterns, and that's what I want to talk about today. And so, just briefly to the background picture here. This is a picture from the Alps, and they can't compete with the Himalayas in terms of height. This is only 2,000 or 3,000 meters here, the mountains. But what you can see is that there used to be all these glaciers here. I mean, every valley basically had a glacier. And so when you look at pictures from the 1930s, 40s, 50s, 60s, this valley here was full of glaciers and snow. And nowadays, this was the summer of 2024. You see there's hardly any snow left and the glaciers are gone. Yeah, and I mean, I think this is a widespread recognition that glaciers actually melt at a rapid rate. And also, what Saurabh was already talking about, that there is indications that higher elevations actually are more exposed to global warming than lower elevations. And which also actually Krishnan in this climate change report for India also highlighted that the climate change in the Himalayas is greater than it is in the lowlands. And one can, of course, ask, why? Why is it like this? And so that's what I want to get into. So it's about, this is a picture here on a map from the IPCC AR6 report. It shows the distribution of warming for 2-degree global warming in the global mean, but it shows very unique patterns. So we already talked about one of them, that the land warms faster than the sea. In the discussions yesterday, we also talked about, why is it actually that these arid regions seem to warm more strongly than the humid regions? And then we also see, of course, that the northern latitudes, they warm quite a bit more strongly than the tropical regions. And there's this big blob here. I mean, this is a loss of sea ice. And so this is the snow albedo effect. And I think these effects here, these can actually be predicted or understood mostly by radiative effects, and not so much the snow albedo feedback. I mean, I think this is sort of this first thing that students usually come up with. They say the snow albedo feedback, is sort of most important. I think it's easy to explain when you want to explain a feedback. The snow albedo feedback is an easy one. But then when you look at the whole sphere of the Earth, the areal extent of snow-covered regions is actually relatively small. And what's much more relevant is actually the water vapor feedback. And this is what we will actually look a bit more into. So part of this has to do with downwelling long-wave radiation. And this is also a topic that when I talk to people outside science, that this downwelling long-wave radiation is something like a mystery because you can't see it. Yeah, I mean, we feel it sometimes when you are aware of how you can sense it. This is something that one can recognize, but it is not something that is so easy and so obvious. Maybe you think it's obvious, but I mean, I think when I actually over the Christmas holidays, I was talking to my parents-in-law and explaining them the difference between heat and radiation and what implications this has for global warming. And they said, "Oh, they had no idea." And they are both scientists with a PhD, not in climate change or in climate science. So I want to look a bit more into the downwelling long-wave radiation. The mechanism behind that. One way to illustrate it is actually something that I found a little toy. You can see it here in the palm of my hand. There's a tiny little infrared camera that you can attach to your mobile phone, and then you can take infrared pictures. And so I'm going through the landscape and making pictures in the visible range. So for example, here, this was the summer vacation last year. You can do a picture of the visible range. You see the North Sea here and the beach and the clouds and the blue sky. And you can also take the same picture with the infrared camera. And there you see the difference in long wave radiation. Because you see a difference in, well, sort of a combination, emissivity and temperature. You see both of them mixed up here. So for example, you see that the water is relatively cool, so it doesn't emit as much. The beach is getting quite warm, so it actually emits quite a bit. And then you can very clearly see where the clouds are and where the sky is blue, because those are pretty dark, right? And so I think this sort of starts to give sort of an indication what's important in terms of this downwelling long wave radiation. When one looks at it more physically, at the level of quantum physics, at the level of atoms and electrons, and the way that that solar radiation or radiation in general is absorbed and emitted, then we deal with quite different mechanisms at the scale of electrons and molecules, because, well, we have an electromagnetic wave, and so this electromagnetic wave needs to interact with something that is charged, with an electron, for instance, because otherwise it can't be absorbed or emitted. And so, for example, when the radiation is very energy rich, then it can actually remove an electron from an atom. This is an ionization, but that usually doesn't happen on Earth. Then it can also break up molecular bonds, so also something electric. This is what we see in the ozone layer. But then in the visible range, electrons can be lifted, they can raise into excited states. This is what happens during photosynthesis. And what the greenhouse effect is about is in the infrared. Oh, this is a German word here. So in the infrared range, that's sort of where the greenhouse effect is active. And there you need to have an uneven charge distribution in your molecule so that an electromagnetic wave can interact with the molecule. Yeah? And so when you have an electromagnetic wave and you, for example, here you have the water molecule, and then, it can sort of start to wobble, or it can start to vibrate and oscillate, and then it can also emit an electric wave again. I mean, this is also what you covered yesterday in the GPS lecture, and why water vapor can be inferred from the noise in the GPS signals, because it absorbs infrared radiation. And so it has something to do with molecular structure. And when you look at the most dominant molecules in the atmosphere, this is actually nitrogen and oxygen, as you know. This is more than 99%. And actually, I talked to a colleague who is in environmental physics, and he taught molecular physics for a number of years. So he actually explained that these molecules are homonuclear molecules, and they are forbidden to have uneven charge distributions. It's a sort of quantum physical effect. So in other words, oxygen and nitrogen, they can't absorb long wave radiation. And so it is only up to water, CO2, and the greenhouse gases. Yeah. And I mean, I think, maybe it's nothing new to you, but I think when I talk to people outside science, they sometimes wonder, how can so little CO2 cause so much climate change? They can't imagine why. And I think that if you communicate that, you say, well, 99% of the atmosphere actually doesn't do anything in terms of radiation. It just sits there passively. Yeah, I think that already gives you a feel for, that water vapor is really important, and CO2 is also important. The next thing is, of course, that we have that water vapor can absorb very well. This is sort of a typical diagram from Wikipedia, but you also have it like in normal textbooks often, where you see the wavelength and the absorption by different compounds here. This is water vapor, carbon dioxide, and so on. You may recognize this figure. Well, the important part is that water vapor absorbs really, really well, except in that range where the surface emits the strongest. Yeah, it's known as the atmospheric window. Yeah, so it's because water vapor doesn't absorb in these wavelengths not so well. This is where the CO2 band sits. And so, in other words, when you have more CO2, then your CO2 absorption broadens and covers the hole that water vapor can't absorb. So far, so good. But now when we think about patterns of climate change, well, some regions are cloudy. When you have cloudy conditions, you don't have an atmospheric window, because water droplets absorb very well across all wavelengths. When you don't have an atmospheric window, then the CO2 peak doesn't matter so much, because water droplets already absorb infrared radiation, so you have a strong greenhouse effect, and an increase in CO2 won't be felt by much. So in other words, we would expect stronger effects of global warming in those regions or at those times when you don't have clouds, when you have blue sky, clear sky conditions. Another aspect is that the atmosphere doesn't have the same amount of water vapor everywhere. When you go into warmer regions, you have more water vapor, and your atmospheric window is smaller, and you cover more of the CO2 absorption band. So this becomes smaller. When you go into colder regions, you have less water vapor in your atmosphere, and you have a broader atmospheric window. And so that means that your CO2 absorption band is more pronounced. And so when you change the CO2 absorption, then you have a proportionally larger effect. Does that make sense? And I think from this you can already infer and explain some of these patterns that we saw recently in a few slides ago, and I'll get into that in a minute. So this is when you have cloudy conditions. This is here a foggy day in northern Germany. Very strong greenhouse effect, and there the CO2 absorption band is not very prominent. There is actually one graphic on Wikipedia that shows that quite nicely, but it's quite hidden. So you have to specifically look for electromagnetic absorption by water vapor on Wikipedia, and you see this graph. What it shows is, here again, the wavelengths from 1 to 10 to 100 micrometer. Again, the peak in absorption, peak of emission of the Earth is around 15 micrometer. Here you see the atmospheric window of water vapor. And when you look at liquid water or ice, you see that they absorb pretty much across the spectrum. Okay, so then if we want to understand or to sort of demonstrate how important this downwelling long-wave radiation is, well, one can see this in terms of how much radiation is absorbed at the surface. Solar radiation in the global mean is 165 watts per square meter. The downwelling long-wave radiation is on average 346 watts per square meter. So it's more than twice, what the surface absorbs. And again, we are since with my colleague here, the astrophysicist, where we try to do sort of popular science and try to break climate change down to communicate to a broader audience. I think a very good way to imagine how important this downwelling long-wave radiation is when you think about the temperatures during day and night, right? I mean, that the daytime temperatures are shaped by solar radiation is almost obvious, right? I mean, when it's more sunny, you get warmer temperatures. In summer, the sun is more intense, you get warmer temperatures than in the winter time, or for you, I mean, I think December, where there's less solar radiation, it's cooler. But then when you think about the nighttime temperatures, if you had no downwelling long-wave radiation, then your nighttime temperatures would be really, really cold. And you have that, for example, on the moon or on the Mars, where the nighttime temperatures get, in fact, really, really cold. Okay, so then I think it's also to get sort of a feel for this greenhouse effect. It also helps to look at seasonal variations. That relates to also what Saurabh already showed yesterday. So we looked into that some years ago with a Chinese visiting student, Yin Tian. So we know very well solar radiation, what the annual mean is, and what the seasonal variation is. So, this is the annual mean. We have the peak in the tropics and less in the poles. And the variability is larger The seasonal cycle is larger in the mid-latitudes. When you look at the annual mean, you see, first of all, it correlates quite well with the solar radiation for good reasons. But then when you look at the seasonal variation, you can see that especially the continental interiors show a really strong seasonal variation in downwelling long-wave radiation. And, this is something that in climatology one covers, that here these regions are the ones that get really cold winter temperatures. Yeah. Because downwelling long-wave radiation is so low. Then that's also something Saurabh already mentioned. We evaluated this semi-empirical parameterization to understand downwelling long-wave radiation. So it takes a shape here, a combination of cloud fraction and a clear sky emissivity, and then it is taking a sigma T8 T2 meter to the 4. This parameterization came up in the 1970s to diagnose downwelling long-wave radiation from weather station data. And so you can actually apply that quite far back in time if you want to sort of infer these fluxes. And you see sort of the main factors that shape variations in downwelling long-wave radiation. So you see, it's cloud cover, it's the temperature of the atmosphere, and this clear sky emissivity, which depends mostly on water vapor. And that's this part here, this emissivity part, sort of an effective emissivity. With the water vapor, this is the atmospheric window. It describes that, when you have higher water vapor in the atmosphere, your window is more closed. When you have less water vapor in the atmosphere, your emissivity is lower, and because your atmospheric window is more widely open. And down here we show sort of the comparison with FluxNet, and Sirius actually works really well. So one can use that to decompose and understand variations in downwelling long-wave radiation. And it captures exactly this point here that, when you have the atmospheric window, I sort of illustrate this here, when you have more water vapor, then the window is less with warmer temperatures. Okay, so what happens now with CO2 is, well, you increase CO2, then you have the water vapor feedback, and your window becomes smaller. And now we can, and this is something that one can actually observe with satellites. This is here from colleagues from the US who deal with these atmospheric radiative transfer. So when you look at the outgoing long-wave flux to space, on clear sky days, you can see sort of certain spectrum, you can see the atmospheric window, and the trend over the years from, this is here from a satellite, this is here from a radiative transfer model, you can see that the atmospheric window actually emits, absorbs more, and the adjacent bands actually emit more. And now we can relate this atmospheric window and these main controls on downwelling long-wave radiation to this map, right? I mean, so we see, for instance, so the arid regions here, that's basically when you are in an arid region, you have less cloudy conditions, sunny days are more prevalent, and sunny days means you see the atmospheric window more often. And so there, when then CO2 increases, these regions should be more should actually experience more global warming because they have more sunny conditions. Then we can also understand why the high latitudes warm more strongly, because they're colder and the atmospheric window is more open, at least on sunny days. And so the atmosphere and the surface sees more of an effect when CO2 actually increases. And related to this, I had a visiting student from China in 2019, I think, Muye, and he looked at weather station data in China. So China doesn't have weather station data that goes back to, I think I talked to one of you yesterday, that it goes back to, in India, it goes back, I think, to 1900 or so, or even longer. But in China, it goes back to about 1955, 1960. But still, you have a good number of decades, right? And so the measurements were quite rudimentary. I mean, this is sort of typical weather station data. So you have Tmin, Tmax, and relative humidity, and you had rainfall. So you don't really have radiation fluxes. But we made an approximation. We said, let's say that days that had rain were cloudy days, and days that didn't have rain are sunny days. And then we filtered or separated the data set according to whether we looked at how did the temperatures behave over the decades with. Yeah, absolutely. Yes. Yes, absolutely. I mean, it's not a perfect classification, but it's sort of like, we didn't know how to do it better, right? And we thought it's simple, and we should still see a signal, because on days where it rains, there should have been at least some clouds, and on days that don't rain, maybe they have clouds, but maybe they are also sunny, right? And just to give you a sense for the climatology, here is shown the so-called aridity index. So in other words, here, I think I showed it yesterday already. So these regions here are deserts, very dry. And down here, you're in the subtropics, humid regions. And so you would expect, well, here you have more clouds because it rains more. Here you have more sunny days because you're in a desert. Then when you looked at temperature trends, so this is here from 1965, I think. I mean, he looked also at consistency of data, the consistency. Sometimes the weather stations moved and so on, so he filtered the weather stations. But then you see here the total trend here in black over the years from 1965 to, what was it here, 2018 or something, and you see the clear warming trend here over the years. The red part is the warming that occurred on days without rainfall. The blue shows the warming on days with rainfall. So you see very clearly that the warming occurred on days where it didn't rain. Yeah. So that were more likely to be sunny. And then, this relates to yesterday, where we already talked about global warming and the diurnal temperature range. So in China, is also very clear, pronounced signal that the diurnal temperature range decreased, and that's because the minimum temperatures increased more strongly than the maximum temperatures. And here too, you can see that these changes occur primarily on these days where it doesn't rain, which we call the sunny days. And one can attribute that, again, directly to this atmospheric window. So when we looked at this geographically, we see here the temperature trend spatially, and we see that, you see some heterogeneity here, but you see quite clearly that the warming occurred more strongly in the arid regions and less in the humid regions here. Yeah, so one can also look at that. I can't quite remember why we use precipitation frequency rather than rainfall rate, but we use precipitation frequency. Maybe because that's the number of rainy days, and so it's like a sign of cloudiness. So you have less rainfall, you have less rainy days here, you have more rainy days there. And so when we look at this and we see the trend, so the more rainy days you have, the more cloudy conditions you have, the more likely you see less of a temperature trend in the data records. So in other words, we can sort of explain these patterns. This one here from yesterday, you had stronger warming on land because the nighttime warms more strongly during the night, which we also have just seen recently in these in the data in China, because you don't have turbulent fluxes at night, because you don't have a heat engine working at night. Then we see this difference between that we have a stronger warming in arid regions, because arid regions are typically sunnier, and that's the atmospheric window. And we also see that the stronger warming Oh no, we didn't see that. Oh, hang on. No, I mean, I think I have another slide for that. Sorry. I mean, I think I got sort of here a little bit out of because now we come to this point where I think this is actually becoming quite relevant, and also what Saurabh was already alluding to yesterday is that, you know, how is that relevant for mountainous regions where you have a high variability in terrain height? Again, here this is the Alps, and so you may remember from Saurabh yesterday that the reason why the temperatures actually decrease as you go higher, the surface temperatures, is because the downwelling long wave radiation goes down. And the downwelling long wave radiation goes down as you go higher up into the mountains, is because you have less of a water vapor column that you see at the surface. And when you have less water vapor in the atmosphere, it means your atmospheric window is more open. Right? I mean, it's a wider atmospheric window. And so in that sense, if there are no clouds, we would expect a stronger warming. But this is something that we are still exploring. This is work in progress. So I'm also showing you here, this is also a sort of personal communication kind of work in progress graph that I want to show you here because I think it sort of substantiates this, at least qualitatively. And as I said, you know, we are working on this. Is that when this was here together with Sergio, actually did the simulations with the radiative transfer model, ECRAT, that's the radiative transfer code of the ERA 5 reanalysis. And so when he varies the CO2 concentrations, so we compared simply the present, I think that this was the one that he had as a control simulation, and he reduced it to 300 ppm. And so we looked at what's the difference in downwelling long wave radiation when we change the CO2. And we did it, you know, we had this parameterization which expressed downwelling long wave radiation as emissivity times sigma TA to the 4. So in other words, when we take the downwelling long wave radiation divided by sigma TA to the 4, then we get an emissivity. And we do this emissivity we look at this emissivity for 394, and we look at it for 300 ppm, and this is the difference that occurs. So this is the difference when we, because of the CO2 effect that so far we have not accounted or included here in this parameterization. And so you see very clearly that when there is less water vapor in the atmosphere, the effect of increased CO2 is much larger than when you have a lot of water vapor in the atmosphere. And again, this is something that one can understand because from the perspective of the atmospheric window, because when you have more water vapor in the atmosphere, then you see less of the CO2 absorption peak, and so you see less of the increase. While when you are in an atmosphere with less water vapor, and these are typically colder temperatures, then the increase of CO2 you see more in the downwelling long wave radiation. And so with this, I think we are quite hopeful that we have a better grasp at understanding this elevation-dependent global warming, climate sensitivity. And so I think I want to close here with this just really brief summary, or where I think this could be really relevant also in the discussions we had yesterday. I found them very stimulating. I think we had very nice discussions yesterday afternoon. So, you know, when you think about climate change and the monsoon system, and, you know, you have these, now I have to remember, monsoon intra-seasonal oscillations, right? Then, you know, you have periods where you have rain and probably clouds, and you have periods where you probably have less clouds. So you could quite imagine that you have also differences in the surface energy balance, and you have differences in surface energy balance change between those oscillations, right? And you also are quite likely to have differences between the non-monsoon season, because they are quite sunny, compared to the monsoon season, right? And I think So I hope you see the point that sunny conditions and cloudy conditions have very different energy balance partitioning, and they also react differently to climate change. And often we just average over seasons, or we do monthly averages, and we don't take account for this difference. And maybe the signal is clearer when we account for these different conditions. And before we average, we actually separate the sunny conditions from the cloudy conditions before we do the averaging. So that's, I think, the one part where this could be helpful. And the other one, I think where this can be also really helpful is with Saurabh's work, is that I think when one knows what the cause is for the temperature control with elevation, that the reason for why the higher elevations are colder because the downwelling long wave radiation is colder, I think this should give also a tool, or should be able to develop a tool to do better downscaling in these highly heterogeneous regions where you have, the mountain tops will basically see more of global warming than the mountain bottoms, because the bottom of the mountain will have more of an atmospheric water column, and so have less global warming than the top of the mountain, if you see what I mean, right? And I think this is something that one could probably incorporate relatively simple by using sort of the fields from a climate model, but then sort of downscale them with, I don't know, GIS or something at a much higher resolution. Yeah, and I think with this, I'm already at my end for this morning. I hope that, yeah, I mean, or, open for discussion, comments. Yeah, thank you. There's one on the left. '20. The temperature change is less. Yes, yes. Yes. Yeah. Well, so it's not cloudy, but it's actually where there was rainfall, right? I mean, so here the precipitation rate was larger than 0.1 millimeter per day. On those days, there was less temperature increase than on those days where precipitation was less than. Huh? Yes, that was our criteria for a day with rain. Yes, yes, that's right. I mean, sometimes it's partly cloudy. I agree. Yeah, I mean, it's not, again, it's not a perfect analysis, but we didn't know better given the data that we had, right? Maybe, I mean, I think if I would do it nowadays, one could also filter, for example, for the diurnal temperature range, right? Because that would clearly have an effect of solar, or see the magnitude of solar radiation, and then one could do that, filter based on that. That would probably be a better filter than this one. This one here. Yeah. Yes. But you are approximating as to yes. Why? Again, the, this will research to develop this relation So I would interpret it this way: the 2-meter air temperature is proxy for how much heat is in the atmosphere. So, like a cumulative measure for how much heat there is at the limit. Likewise, it's sort of the 2-meter air, the 2-meter water vapor proxy for how much water vapor is in the water. Again, they're not exact, but you look at 5, or 5 is not shown here. So I think the assumption that is again, it's not precise. I mean, it's not like the atmosphere emits serious radiative temperature, right? So, I don't have an answer, except to say that people is always to be watchful for what's a real observation.
The emissivity of cloud is perfectly one, right?
Yes. And this is again probably right.
When you talk of non-gravity, ultimately is also boils down to absorption by the surface. You know that the difference in emissivity is dependent upon the time of the surface also. So for example, in desert it can go as low as 0.7. In vegetation it can be as large as 0.99. So that part was not necessary.
No, I didn't mention it. We didn't include it either. Yeah, so I mean that's also that's a good point.
Yes.
Actually as simple as possible, right? And then we can always go from the things zero.
Hi. Yeah, so my question is over the oceans, especially over the subtropics, where we have the marine stratocumulus clouds. So they are occupying the very lowermost part of the troposphere and not precipitating clouds. And just above it on the pre-troposphere, it's all dry. So there's no moisture, as you say. The atmospheric window is quite available for CO2 absorption. So, sorry? Above the clouds. Yes. Yeah. So in a changing climate model, simulations show that these clouds are going to decrease because the long wave radiation emitted from the cloud tops is no more efficient to drive turbulent processes and cloud formation, since the downwelling cloud long wave radiation is going to increase. It is going to balance or kind of collapse the clouds. So what is your opinion when that comes to sensitivity? Because a large area will get exposed to the open, dark ocean surface.
I haven't thought about that, but I mean, it sounds fascinating. Yeah, I mean, I think I have to think about that. So I can't tell you something spontaneous, but I mean, I think it sounds interesting, right? I mean, and it can have quite a strong effect.
So the question is regarding the subtropical oceans. So we have large areas of subtropical highs, and the spatial coverage of stratocumulus cloud cover is quite large. They occupy around 20 or 25% of the surface area globally. So in that case, these clouds usually are survive because of the cloud top radiative cooling, long wave radiative cooling. That keeps the cloud going. In a warming scenario, the downwelling long wave radiation from the pre-troposphere is so high that the long wave cooling or the upwelling long wave radiation gets cancelled out. So that can lead to cloud dissipation and then expose the quite dark ocean surface. So in that case, the sensitivity of the climate system is expected to be much more large.
I think what I'm thinking about is something that we can talk about in the afternoon. Actually, is that when you think of a cloud, the stratus cloud, right, and it cools by emitting radiation from the top, that drives a heat engine, right? Because not by heating from below, but by cooling from the top. It may not be as powerful as when you have dry convection in the desert, but you still generate power and motion, in this case, sinking motion. And I think this is exactly what you talk about, right? I mean, so in other words, you need to have a temperature contrast between the cloud top and the ocean surface. And so when you have more greenhouse gases in the clear sky above the stratus clouds, then you warm the top and you make the stratus cloud less powerful. And that's why you say it dissipates, right?
There are papers using simulations showing there's a tipping point.
Yeah, I can.
CO2 concentration.
Mm-hmm. Sounds plausible. Yeah.
Seems to have a larger impact on the climate sensitivity.
Yeah, I can imagine. Yeah.
Thank you.
Yeah. Yeah, thank you.
Morning. We are now back this session. So now our next lecture will be on Earth system, IITM's Earth system model. It's a very prestigious asset of our country itself, and its overview, biases, and discussions and scopes for improvement, and it will be delivered by our scientist, Dr. Sandeep and Sethi. Sandeep.
Good morning, everyone. Myself, Sandeep Narayan Shetty. So today I will be giving a talk on the IITM Earth System Model. So we'll be covering some overview of the model, followed by biases and certain discussion and some research from our group, and also the scope of improvement to how to proceed it further, and what is our timeline and how do we work there. So this is our group. So our objective is to understand the science of climate change, including the detection, attribution of climate extremes. And we have, like just now Dr. Datta mentioned, we are working towards building in-house capacity in climate modeling. And we contribute to IPCC, CIMIP, and National Climate Change Assessment Report as well. And moving ahead, so this is the timeline, and this is the history from where IITM Earth System Model development started in 2010. This was adapted from CFS V2 under the Monsoon Mission Program, and it was then adapted to develop Earth System Model at CCCR. And then in 2014, the first prototype version, that is the Earth System Model version 1, was developed. We have incorporated the interactive ocean biogeochemistry for P1 model, that's the ocean model, ocean component. And from there, we moved to Earth System Model version 2 in 2018, and that we have participated in CIMIP 6. For people who are unversed, it is Climate Model Intercomparison Project 6. So there were similar projects earlier, and it's a cycle. And right now, after CIMIP 6, it moves to CIMIP 7. And we had a radiatively balanced framework for this long-term climate simulations. And we have improved coupling between the components after the intercomparison and project, and also incorporation of this interactive ocean biogeochemistry. We have partial grid implementation and also a CIS model incorporation. And after 2018, when this model was freezed, we completed the CIMIP 6 cycle, and we have disseminated the CIMIP 6 data through the ESGF data portal. And again, for unversed, is the Earth System Global Federation data portal. And this entire process took us 3 years, that is from 2019 to 2021. And again, like I was mentioning, after CIMIP 6, now we'll be moving to CIMIP 7. So the current version of the model, that is IITM ESM V3, we are working on. I'll be showing you what are the developments we are doing and also certain research topics. So this is our national contribution, which is the assessment of climate change over the Indian region, a report of the Ministry of Earth Sciences, Government of India. And also we contributed to the IPCC and the Climate Change 2021, the Physical Science Basis book. And here I show you the global mean surface air temperature from 1850 to 2014. That is the cycle until the historical simulations of CIMIP 6 were concerned. And the highlighted is the IITM Earth System Model. And after 2014 and 2021, where we have incorporated all this and participated in CIMIP and IPCC, now currently we are developing the IITM Earth System Model version 3. And this has changed in the atmospheric grid, that is a TCO, that is triangular cuboid octahedral. We have an Indian land use land cover incorporated. We have river routing incorporated. We have an improved ocean. And also we are working towards representing the glacial ice that is from Greenland, and also Himalayan glacier, which is one of the very important component, that's the third pole. And we're working towards incorporating this as well. So we have also incorporated the time varying aerosol interactions into the model. So I'll be talking about each component in brief and then focus the other things as well. So firstly, coming to the atmosphere. So like I was mentioning, it was T62, that is almost 190 kilometers, approximately 2-degree model we had. And then right now we followed the ECMWF IFS framework. We incorporated TCO 126, which is around 67 kilometers in the tropics. And we get, for the same computational, we get a higher effective resolution near the tropics, and it's computationally efficient, and we get a better resolution, which we are looking forward for. And similar improvement we have done for ocean as well. So we have increased the resolution of the ocean within the tropics. We had 0.33 degree earlier, and now it is 0.25 degree, that's a quarter degree. And these are the river destination, like I was mentioning. We have a river active river routing. So the precipitation minus the evaporation minus runoff over the land is routed into the nearest destination point, and then it is discharged into the ocean. And we also work with the biogeochemistry component. The shaded is the chlorophyll here, and we also work on the glacier modeling, like I was mentioning. And we have ideas to include do water availability module as well, and also we have another set of people who work on the high resolution global atmospheric model, which is around 27-kilometer version of the model. And we have a team which works on paleoclimate modeling. That is, we work on PMIP simulation. That is like we try to simulate the 127,000 years ago. That is the last interglacial, and also mid Holocene. That is 6,000 years ago. We do that experiments as well, and we have a climate data analysis tool. And building upon the aerosol component, we have incorporated the CMIP-7 climatological aerosols. The single scattering albedo and the asymmetric background is also represented spatially varying from comparison to CMIP-6 and CMIP-7. So we have better representation of volcanic eruptions in CMIP-7 and also better representation of natural aerosols and aerosol radiation interactions. We are working towards the implementation of Indian land use land cover data. So we have changed it from 13 types to 24 types, and we have seen certain changes from the USGS land use land cover and also the NRSC land use land cover. We have adapted the NRSC land use land cover into our model, and then we see there is a change between this dryland cropland and also irrigated cropland. And also the savannas, which were represented by USGS, is now deciduous broadleaf forest. And we have seen that changes, and they also improved the better simulation of the climate over Indian landmass. Also, we work on the glacier modeling, like I was mentioning earlier. So this is the work which we are doing for Himalayas. So we run an OGGM, that is the Open Global Glacier Model, and we set it up over the Western Himalayan region. And then we would like to add this glacier melt from the model. And this is forced with the historical simulation and the projections of IITM ESM. So it takes both the temperature and precipitation from IITM Earth System model, and it is given to OGGM, and then it calculates the glacier melt. The ablation, accumulation, and the surface mass balance is computed. And then we would like to incorporate that melt into our IITM ESM and rerun the process to understand only the influence of the glacier melt in a warming scenario. So coming back to what we do in our model, and these are the results. This follows the results now. So for any climate model, we'll have to have a stable ocean setup before coupling. So we have run a standalone version of MOM4 P1 for 500 years, and we see the total kinetic energy where it is stable. And also we do the same for the atmosphere for 50 years, since atmosphere adjusts faster. So we take the stable ocean setup and the stable atmosphere setup, and then we run a pre-industrial control, which is spin-up of 800 years. So this is how the balance in the model will be checked, and you see the top of the atmosphere flux. So when that is stable, that implies your model is getting stable, and also we see the surface air temperature, that is also stable. So we have around 14 degrees in the surface temperature in the pre-industrial control simulation, and also we observe the sea surface temperature and sea surface salinity, both are stable. And also the another important climate indicator is the AMOC, that is the Atlantic Meridional Overturning Circulation. So that also is at around 18.5 Swedrup, which is stable. And also we have seen the Arctic sea ice, and the Northern Hemispheric sea ice also is found to be stable. But with this benchmark, we moved ahead and we tried to understand the biases in the model. So this is the version 2 of the model which participated in CMIP-6. And we see there is a cold bias over the Indian Ocean, and we see that there is a reduction in the cold bias in the version 3, which is the high resolution now. So when we say V2, that is IITM ESM V2, it is a CMIP-6, 67-kilometer atmosphere and a low resolution ocean. And V2.51 is an intermediate version, and V3 is the CMIP-7 version, in which we have both the high resolution atmosphere and also high resolution ocean. So we also see that there is a decrease in the Southern Ocean SST bias. So we had a huge Southern Ocean SST bias, which has improved now. And we have also calculated the regional SST skill from global, tropics, Pacific, Indian, and Atlantic across the versions from V2, V2.1, and V2.3. So we see there is a lower score in the version 3, which is indicating smaller biases. And we have seen other improvements as well, which follows. So like I was mentioning, the SST, we also see a changes in the salinity. So the North Atlantic freshening bias has also reduced here. And also we have seen a change in the Bay of Bengal and North subtropical Pacific salinity has reduced. And this is the subsurface for Indian, Pacific, and Atlantic region. We see the subsurface visibility also in the three basins has reduced from version 2, 2.1 to 3. So we are well representing the subsurface structure and also the surface structure in the current version of the model. So this gave us an encouraging idea. And then we have also checked the thermoclines in the T20. We see they are also very well represented in the Indian Ocean. So that actually well represents your Indian Ocean dipole, and then your Indian Ocean dipole monsoon interactions also will be improved. So after doing this, then the other indicator we wanted to see is the AMOC, that is the Atlantic Meridional Overturning Circulation. So this is quite important because it has a potential role in changing the location of ITCZ and also the North Atlantic storm tracks and the North American and European summer climate and also the sea level rise. So we wanted to see how is this represented in our model. And the people who are unversed, so there is this Atlantic Meridional Overturning Circulation is the branch of the thermohaline circulation, which transports the warm waters from the tropics towards the pole. And it actually constitutes around 25% of the heat transport and the salt transport from the tropics to the poles. So the last thousands of years, if you analyze, there is a warm mode, cold mode, and an off mode here. So warm mode, you see an extra intrusion of the warm waters in the Atlantic towards higher latitudes. And in the cold mode, it doesn't reach that high latitudes. It reverses back and it's the North Atlantic deep water. And in the cold mode, when it's off mode, there is a large scale ice discharge. That is in the last interglacial where there is a large ice discharge. Completely ice gets flushed into this Atlantic. And you see there is an AMOC collapse because of the changes in the stratification. So what are these reasons? Like why should AMOC change and what is it happening in the recent decades? So a paper by Ramstorff et al. 2015, they have shown that the AMOC from the index of the temperature, that it is declining in the recent decades. And if you see the surface temperature trends from 1900 to 2015, you see a hole, it's warming hole here. This is because of the weakening of AMOC. So if all the heat is not getting transported from the tropics to the poles, so you will definitely see a cold blob over here. So that is a subpolar dial location. And this is very, very important. And this is an indicator to understand the changes in your AMOC. So researchers have incorporated an array at 26.5 degree north, which is called rapid Motka array. And if you see from 2004, that also shows a decline. So if such a system gets collapsed, what will be its climate impact also? Our group does a research about that. Firstly, we have also seen there is a paper by Swelek in 2017 in which they try to understand that the Arctic sea ice, when there is a large scale warming, which is happening right now, where there is an Arctic amplification. So there is a large scale ice melt. It loses the fresh water, gets melted, and then comes into this region. It causes the fresh and the not so dense water forms a very, very stratified column over the Atlantic, and then it reduces the sinking branch, and that's how the AMOC declines. Sorry. Yeah. So then we compared. So now that we had an idea about this importance of AMOC, so how is it represented in the model? And can we understand a bit further if such an impact of AMOC, where there is a decline in the AMOC and also where there is a complete shutdown of the AMOC, what would be its impact on the monsoon, which is the staple source of food for our system? So here I show you the AMOC from the GODAS, the Ocean Data Assimilation System. So the red one is the North Atlantic deep water, which is quite transferring towards the north, and this is the Antarctic bottom water. This is the version 2 we had, and then this is the version 3. You definitely can see an improved representation of the AMOC. So by simple understanding, if you have a better heat transport towards the north from the tropics, you definitely expect a reduction in the temperature biases over the North Atlantic region, which you might have seen in the SST plots in the earlier figures. And since this AMOC is quite important for determining the location of ITCZ, it would be good, and it's presumptuous that when you have a better AMOC, you will have a better representation of ITCZ as well. So this is the AMOC, like I was telling, we had a stable AMOC, and also we have a good monsoon representation in the model. So we tried to do certain experiments from our model, and which we have done some experiment, which is FAF experiments, which I'll be explaining you in the next slide. So these FAF experiments are when the flux anomaly forcing model intercomparison project experiments. So what we do is we take, when you run a carbon dioxide concentration increase with 1% per year, and you see from 280 it reaches around 560 ppm by 70th year. So what we do is we check the difference between the surface heat flux, the net surface heat flux average between 61st to 80th year of this section minus your pre-industrial control. And then we average it across 10 models. And this gives us indicator, this is the net surface heat flux anomaly, which is used as forcing. And also we do the same for the precipitation minus evaporation, because both temperature and salinity can modulate your density in the Atlantic and cause changes in the AMOC. So this is the basic protocol we follow. We have introduced three-dimensional ocean tracers, which are the added heat and the redistributed heat. So we see that the changes going to the results. So when we had a control experiment, this is the AMOC, like you've been seeing for the past 2-3 slides. And this is from the FAF heat. When we have incorporated the heating, so this is the heating which we have incorporated. So by virtue of the heating, it changes the stratification, it changes the density gradient, and you see there is a reduction in the AMOC structure here. And similarly, we have done the precipitation minus evaporation, that is freshening. So that also changes your density, that also changes your stratification. So you see that the heating actually reduces your AMOC more when compared to the freshening. So here I am showing you the plot. The blue plot is from a control simulation where we had a very stable AMOC. And when I have incorporated the heating, we see there is a decrease of around 50% in the AMOC, and also FAF water is a 25%. That is when we are doing a freshening. And then these estimates were actually cross-verified across the other models which participated in FAFMIT, and we are in the same range which they have shown. So we try to understand what is the possible physics and the mechanism which is doing all this business. So here I'm showing you the ocean heat transport. So the blue curve is the ocean heat transport from our control simulation, and the red curve is from the FAF heat. So you clearly see there is a reduction in the ocean heat transport by virtue of the decline of AMOC. And for a climate system, whenever there is a decline in the poleward ocean heat transport, it gets compensated by the atmospheric heat transport. So when we see that the FAF heat, there is a significant net northward cross-equatorial energy transport which is weakened. And then when this green curve, this is the difference between the blue and red. So you see there is a reduction in the oceanic heat transport, which gets compensated by changes in your atmospheric heat transport. And this atmospheric heat transport determines your location of ITCZ. So we have done few other experiments as well. And then this case, what we have been discussing is just a change in the AMOC alone. It's an idealized case. But in general, also the carbon dioxide concentration is also increasing. So that also can cause a warming. That also can change the Arctic sea ice. That also can cause freshening. That also can cause an AMOC weakening. So we try to understand the balance between these FAF experiments and the real case, that is the 1% CO2 experiment. We see that there is a large scale, because of the weakening of the AMOC, we see there is a large scale north-south hemispherical temperature gradient, and that has changed the location of ITCZ, that has changed the mean monsoon Hadley cell. The Hadley cell has weakened, and then we have seen there is a changes in the precipitation as well. So these are the precipitation, and we see that the moisture flux over the Indian region has reduced. And then the contrary in the 1% CO2 experiment, by virtue of the available moisture, we see though there is an increase in the 850 HPA moisture flux, though the precipitation showed a decline for us. So we have concluded that both fast heat and transient CO2 experiment reveal consistent results of weakening South Asian monsoon circulation with the decline of the AMOC. But by virtue of the enhanced moisture availability, you see an enhanced precipitation over the Indian region in 1% CO2 experiment. So now coming back to our other diagnostics of IITM ESM V3, like I was mentioning, our precipitation, this is from the GPCP and the ESM V3 and also ESM V2. And we see there is a better representation of the tropical land precipitation in the current version of the model. And also we have done for the same for the winter precipitation, that is DJI. You can clearly see over the Amazon region, we have improved, lot of precipitation has improved in the recent times. And then we check for our region as well, what is precipitation bias for the version V2 and V3 with comparison to the CRU rainfall data here. And this is the bias. So in the previous version, we had large bias, dry bias. And the current version, we have improved that bias by virtue of the resolution, and also the large scale circulation has also improved. So, and this is the seasonal cycle. And we see that there's a June, July, August, September peak in the rainfall. And this is a red curve that is from the ESM V2. And this is the blue curve, ESM V3. We see an enhanced, improved representation of precipitation and also reduction in the bias. And then we compared it with the other CIMIC models where we stand. So I've taken around 35 CIMIC models, and we see that this is a score for rainfall, and also wind also we have done. And we see from 0.63 to 64, we have 74, we have improved the score. That implies we had a better skill in representation of monsoon, and also we have a better representation of wind shear as well. That is the U850 minus U200, and this has this development also is one of the important monsoon. Since we are a monsoon centric model, this is very important, and we are getting better results in the current version. And later we have also seen, because of the changes in the precipitation and because of changes in the latent heat which gets released into the atmosphere, we check the upper level circulation from 850 HPA and 200 HPA. We see that there is the improvement. We can see the 200 HPA geopotential height has definitely improved here from version 2 to version 3. And also because of the changes, we also see there is an improvement in the temperature. This is the vertical from 1000 to 100 HPA. You see there is a change in the temperature as well. And this is the tropospheric temperature gradient, which is very important for our monsoon to propagate and sustain. So we see there is an improvement in that as well. And then later again, with this metric also, we compared with the other suite of models from around 35 to 36 model. And we see that our RMSE has reduced. That implies again a smaller bias in the model across many. We have done the precipitation historical, precipitation global, and also precipitation Indian region as well. And also we did for U850, U200 as well. So we see there is a consistent improvement in our model. And we see a lower RMSE scores which we are getting in the current version of the model, which is indicating a smaller bias. And we are going towards a well-represented system. And then one of the other important parameter to verify is the teleconnections to monsoon. So we had two important ocean drivers, that is the Indian Ocean Dipole and also the El Nino Southern Oscillation. So we see that our ENSO and also the IOD monsoon association is well represented in the model. Another important aspect which we look at is the sea ice extent. So we have a better representation. So the blue curve is the CIMIP 6 version of the model, and the red curve is the CIMIP 7 version of the model. So we have a better representation of sea ice as well in the Arctic. And also we see that the RMSE has substantially reduced in this version of the model. Our ACC is also, that's the Antarctic Circumpolar Current, which is also very well improved and it's well represented in the current version of the model. And the mid-latitude wave train. So there is a polar and the monsoon teleconnection to get it well represented. The mid-latitude wave train has to be well represented in the model. That is also well represented in the current version of the model. And we also work for the biogeochemistry. We see the Arabian Sea and Bay of Bengal. In this CMIP 6 version, we have checked, and we see this is from the comparison with the gap filled product of chlorophyll. And then we see there is a changes in the productivity, and we are currently working on the improvement in the productivity because of the changes in the circulation in the Arabian Sea and the Bay of Bengal. And also this was compared to the bobble array here, and then we see that there is a deep chlorophyll max in southern Bay of Bengal is also well represented in the model. And these are few research highlights from our model where we work on the teleconnections and polar connections, and also aerosols and sea level rise, and also many physics parameterization, and also paleo models as well. So when it comes to the next, next what we are going to do, so we'll be doing CMIP 7 and ITCZ AR7. Our main focus is to understand, detect, and attribute the climate extremes. And from 2027 onwards, we'll be working for the next generation of ESM, where we will be trying to incorporate the dynamic vegetation, interactive aerosol, improved representation of ice sheet, and carbon cycle. Way forward, we would like to develop a hybrid high resolution ESM, which is having physics plus AI/ML and also contribute to climate services. On that note, thank you everyone for listening.
Yeah, hey, thank you very much for this nice overview. I wonder, what do you think are the main reasons for why India is drier?
Okay, so firstly, there are two things. So the resolution of the model, which is quite important to understand the processes. And when we have changed the resolution from 200 kilometers to 67 kilometers, the processes are well understood and well seen in the model, where we see that the dry bias has reduced definitely. And also, it's not only this, there is a large scale north-south hemispherical temperature gradient, which is quite important. So that is again dependent on your oceanic heat transports, atmospheric heat transport, and also the location of ITCZ. So when you get that is what we have been seeing in the consistently in our model, where we can improve the large scale circulation and also the regional circulation together, where we see a reduction in the dry bias in the model. So ideally, we had a dry bias earlier. That dry bias is consistently reduced here. Yes. Yeah, the orography is again well represented in the model. Yes.
How are temperatures?
We had a cold bias, but I think that figure is there with us. I can share with you, and then we can discuss on that. Yeah.
Yeah, thank you. You also check the other surface energy balance components for land, whether they are well captured against observations. Because I think cold bias in temperatures could be linked to how land models solve surface energy balance.
My colleague Priya is there. I think she can better answer this question. Priya, if you have checked the land atmosphere interactions.
but after increasing the resolution and incorporating the new landing stand cover, there is an improvement in the precipitation. But the other things we need to check.
Thank you very much.
Thank you.
Next year.
Good morning, I guess. We are not yet at 12. Yeah. So the topic the organizers gave me was understanding of ITCZ and gaps. And as I understand, a lot of students are attending. So I'll be talking of mostly, initially, I'll be talking about the fundamentals of the ITCZ. Then I will be showing some results from one of my PhD students. He's working on the ITCZ, some of his work where we are trying to look how the anthropogenic forcings are changing the precipitation, the Hadley circulation, and the ITCZ. Yeah. So when anytime we take a snapshot of our Earth from space, be it any season, be it any angle, we see this large-scale organized cloud bands that span across the entire tropical region, confined to the equatorial around 60 degrees north. So, and when we zoom into this, these are basically mesoscale convective systems. We are organized into weather systems, and they are organized as rain bands across thousands of kilometers. So this is a visual representation of atmospheric energetics. Now, when we look into the precipitation, so this is the precipitation map, the annual mean precipitation. The blue here shows the amounts of precipitation. So the most heavy precipitation over the Earth, it takes place over the equatorial region. Over the Indian Ocean region, it is located a bit south of the equator, but over the Pacific, which is basically the ocean temperatures are controlling, it is located just north of the equator. And when we do a zonal mean, we find that the maxima is located just north of the equator. So this is the intertropical convergence zone as we know it. And what happens is basically the winds, the large scale circulation, the subtropical highs, force the easterlies, and there is the moisture convergence, the warm moist air converges over this equatorial region. It is forced upwards. We have very high vertical velocities over this region, and then the wind diverges. So this ITCZ is very intricately linked with the overturning circulations, that is the Hadley cell and the Walker cell. So any change in the Hadley and the Walker will be reflected in the position and dynamics of the ITCZ, as well as the change in the ITCZ due to the energy of the system will reflect in the Hadley and the Walker circulation. So just to show the seasonal migration, because the energy that drives the Earth's circulation is sun's radiation. So, and it has got a seasonal cycle. So as we go from January to October, like the winter season to our pre-monsoon, as we say, so we see that ITCZ is located just south of the equator because the sun is over the southern hemisphere. Then as we go to the summer season, the boreal summer season, the ITCZ migrates north. Now, a very interesting feature happens over the Indian region because during the June, July, August, September, we have the monsoons. So the ITCZ moves over the continental region. That is the only region where it moves from the oceanic southern Indian Ocean to the northern continental regions. And by October, it migrates back towards the equator and is located again a bit south of the equator. Here we can see the two sectors, the Pacific sector and the South Asian monsoon sector. So this is the zero line, and this is the seasonal from January to December, the annual cycle, how it migrates. So we can see over the Pacific sector, mostly the ITCZ is located just north of the equator, and we have this easterly convergence over this region. But when we come to the South Asian monsoon sector, we find that in the initial months, January to April, when we transition from winter towards the pre-monsoon and then the monsoon, we find it is located, the maximum rainfall band is located south of the equator. Then as we have the monsoon onset and as the summer season sets in, we have this land sea temperature contrast. We have the progression, northward migration of the organized rain band, and it sets over the Indian landmass, where it stays basically supported by the diabatic heating and the circulation. So along with the solar heating, there are other factors which control the migration and movement of the ITCZ locally in different regions. And finally, after the monsoon, as the monsoon withdraws, the ITCZ comes back south of the equator. And of course, the SST plays a very major role. The SST, the sea surface processes, and the gradients of SST. So if we look into the annual mean SST, we know the SST is maximum over the equatorial region, especially we have this high SST over the Western Pacific, and we have this strong east-west gradient. So the ITCZ also is located over this high SST maxima, and the S interactions and the oceanic processes also control the position of the ITCZ. Now, since radiation is a primary driver, the major driver, therefore, the interhemispheric temperature contrast also controls. It is very highly linked to this migration of the ITCZ. And when we look into past records, so this is kind of, we are going thousands of years backwards. So this is the time when we had this maximum temperature expansion, the Holocene, wherein the northern hemisphere was warmest and the southern hemisphere was coolest. So this black curve here, it represents the temperature gradient, the north-south temperature gradient. The red lines here are the migration of the ITCZ. So it goes north, so upward is north, and southward is like it is drier. So north is wetter and the south is drier. So we can see as we come from the Holocene towards our present day, as the planet has cooled, the ITCZ also has migrated from north to south. And this blue is the Indian monsoon, superimposed is the Indian monsoon. And we can see even the Indian monsoon follows what the ITCZ follows. So basically, as we come from Holocene towards the present day, we have the Indian monsoon precipitation goes from wetter to a more drier phase. And it is also reflected, the top panel here is from the Sahel, because Sahel is located at the heart of Africa and is very directly linked with the north-south temperature gradient that first reflects in the Sahel rainfall. So we can see this black curve here is the temperature contrast, the north-south temperature contrast, hemispheric temperature contrast, and the blue line is the Sahel rainfall. So it very well, it goes with the increased temperature contrast, increased Sahel precipitation, reduced temperature contrast, reduced Sahel precipitation. Now, as I said already, the ITCZ is strongly linked with our Hadley circulation. And Hadley circulation can be seen from the meridional stream function. So the position of the ITCZ can be defined from the meridional stream function. So when the stream function, the meridional mass stream function, the mid-level meridional mass stream function, psi becomes 0. It is the position of the ITCZ. And where the ascending motion changes to descending, basically where the slope becomes 0, there is the width of it defines the width of the ITCZ, the extent of the ITCZ. So the north-south extent. And then using that north-south extent and the area, we can find the intensity. So the psi divided by the area gives us the intensity of the ITCZ. So as we already had discussed, we have this easterly winds converging. We have this warm moist air, which then rises up very high vertical velocities. That is another parameter, like the maximum in the vertical velocities are the region where the ITCZ occurs, the position of the ITCZ. And in the upper level, we have this cool air which diverges. So the energy is higher in the upper level, and that energy transport happens by the upper level winds. So we have southward transport of energy from the ITCZ towards the southern hemisphere, and there is another branch which diverges towards the northern hemisphere. Now, so since it is controlled by this energy flux divergence, so that the energy flux equator also gives us the position of the ITCZ. And the position of the ITCZ, it is controlled by the factors, that is the transport of the moist static energy, the equatorial transport of the moist static energy, and the net input that goes into the equator, the energy input that goes into the equator. Now, when the northward cross equatorial energy transport, so basically when the energy transport changes across the equator, if we have less northward equatorial energy transport, that is means if we have more southward energy transport, our upper level northerlies are stronger, then the ITCZ position, then our ITCZ position, it can shift northward. So this cross equatorial energy transport, it controls the position of the ITCZ. Also, if there is strong input of energy in the equatorial region, for example, take the case of an El Nino, when the equator heats up, then the ITCZ shifts southward to its normal position. Now, when we talk about climate change, how will because the energy in the system is changing, so what will be the changes in the position or the intensity or the location? So in this study by Brian et al., they have looked into future CMIP simulations. This is a CMIP 5 simulations, and from there, what they have done is they have looked into the location, the width, and the strength. What they found was the location is slightly north of its normal position for end of century simulations, and the width also changes. So basically the width, it is becoming more narrower, and since we already know that global warming, the SST gradients are changing and the circulation is weakening. So here you can see the delta omega, that is the change in the vertical velocities, and we find that there is more reduced upward motion, so it is positive, so change is positive. So basically there is a weakening of the circulation, the strength of the ITCZ is weakening, as well as it is becoming narrower. So this is reflected in the scatter plot here, where this is a function of change in strength and the change in width, and these are all the CMIP models. So mostly all the CMIP 5 models showed that the width is reducing, as well as the strength of the ITCZ is decreasing. But we have to keep in mind that all the models are biased towards El Nino, and all the models are biased towards a differential SST warming. Now, in this paper, what they tried to do was, that was the zonal mean position of the ITCZ. Now, what they have tried to do in this paper, they have looked into the geographical variation of the ITCZ across the latitudes. So this is across five decades they have done. What they find is, over the Indian region, over the Eurasian and the Indian region, when they looked into the change from the CMIP models, for every 5 decades, there is a positive change. That means it is moving northward. Wherever in the East Equatorial Pacific and this American region, the American subcontinent region, they found that the ITCZ is moving southward because of the changes in the SST. Because as we know, in the global warming, the Eurasian continent is warming much faster than the ocean. So the energy in the continents is much higher than the Indian Ocean region. So the ITCZ moves northward, and it is seen in the energy flux equator shift also. So the energy is higher in the north and lower in the south. So the ITCZ, basically the southward energy transport. So the system has to transport more energy southward. So the ITCZ moves northward, and the northerly winds are strengthened. And over the eastern equatorial Pacific, because of the differential warming, we have a southward shift of the ITCZ. Now, this was a very interesting experiment done by Haywood a couple of years back. So since we were talking about the interhemispheric energy gradients, and one of the primary contributor of these gradients are albedo. Based on clouds, aerosols, whatever, we can change the albedo. So whenever there is any change in aerosols, clouds, it will reflect in the reflected solar radiation. So that will also have an impact on the position of the ITCZ. So what they found was, in the top panel, this is the ERA reanalysis. and this omega gives you the position of the ITCZ. So this is an experiment conducted during the summer monsoon season to look into the monsoon precipitation actually. So the ITCZ is located here in Era, around just south of 10 degree north, and we have this tropical easterly jet. Now, when they looked into their UK ESM, and I am sure in most of the CMIP ESMs, we will find that the ITCZ is located far to the south of that position, the climatological position. It is located far to the south. And also the easterly jet is located to the south. So what they try to do now, how to improve that? So what they try to do, they injected stratospheric aerosols in the southern hemisphere. So basically they cool down the southern hemisphere more. So they are creating a north-south hemispheric energy gradient. And what they find is, here is the bar plot from the energy transport. So this is the atmospheric energy transport. So earlier they had positive here, which due to the stratospheric aerosols, it changes. So we have now a southward energy transport, which actually shifts the position. So this is the position of ITCZ when you have this, when you are doing a stratospheric experiment minus the HIS. So they found that when they included the stratospheric aerosols in the southern hemisphere, artificial inclusion, they can shift the ITCZ position northward, and they reduce the westerly bias in the winds, and the even the easterly jet got corrected. So this basically happened because while the upward branch of the Hadley cell, it transports energy, the lower branch of the cell, it does a cross equatorial moisture transport, which produces more convection, and it produces more rainfall over the northern regions. Now, coming to the gaps and challenges, we all know about this ITCZ bias, the double ITCZ bias. So all the CMIP models, including our model, Sandeep just showed, there is warming over the southern ocean region. And so this is basically the rainfall from GPCP and rainfall for CMIP 5. So all the models have this double ITCZ, what we call, and there is more rainfall over the southern region. Now, when we look into the radiative forcing, the observed radiative forcing, the shortwave cloud forcing from observations and models, you can see from observations, there is this clouding over this region which reflects the solar radiation, which cools down the southern hemisphere. But here what we have is, in the models, we have a very warm bias, we have very less clouds over this region, and we have more input of energy. So when we have too much of input of shortwave radiation over this region, again, it pulls the ITCZ southward, and we have it. It contributes to the production of this double ITCZ bias. Now, for Khalik, what we were trying to do is we were trying to see, because we have the solar radiation clouds that are in-house, but then we have, in the recent years, we have, due to the anthropogenic changes, we have put in a lot of carbon dioxide, a lot of aerosols into the system. Now, how does that impact? Does that impact the ITCZ? Does that impact the precipitation? How does it happen? So for this study, we have taken the winter monsoon months, and the idea was actually, because we know that there is some subtropical drying happening. So we were trying to see whether the anthropogenically forced changes contribute to that. So this is the DJF climatological ITCZ. We can see that it is mostly to the south, especially over the Indian Ocean. I'll draw your attention to the Indian Ocean region, because this is basically our point of interest. Now, if we look into the trend pattern of the precipitation for the DJF, so you can see that there is the blue curve, blue shading here shows the increase in precipitation. And we can see that the southern Indian Ocean, the precipitation is increasing. So basically the convection is increasing over the southern Indian Ocean. So when we look into the observed changes of the Hadley circulation, we find that there is intensification of the Hadley circulation, and we find there is a branch which is intensified. This is contributed by the Indian Ocean region, where we have this upward motions. And when we look into the long-term change of the Hadley cell, we find there is an intensification of the Hadley cell over the period of 60 to 70 years. It's analyzed from 1950. So this is again the rainfall trends, and when we look into the meridional vertical mass flux, the trend in the transport of energy, we can see that there is an increased transport over the East Equatorial Pacific and a decreased transport over the Indian Ocean region. So basically that shifts the rain bands. So now, where does aerosols and GHG come? So what we did was we did some experiments using IITM ESM, the version 2. And here we did an experiment where we had the basic 1850 conditions, aerosols, greenhouse gases. So that is the PICTL. And then what we did was we have in present day aerosol conditions where we have the natural and the anthropogenic of the present day, but we keep the carbon dioxide at the pre-industrial levels. Then we have a greenhouse gas experiment where we have the greenhouse gas at the 2005, that is the present day condition. And we have a combined experiment where we have the present day natural and anthropogenic. So now when we take the difference between these three experiments, AER, GHG, and the combined with the pre-industrial, we can see how the aerosol or the GHG forcing or the combined forcing, it changes the circulation and the precipitation. So this is again coming to the model rainfall and the observed rainfall, and we find at least over the Indian region and the Pacific, the model captures the ITCZ position well, and that is our region of interest. And so this was again the observed rainfall changes. So when we looked into the position of the ITCZ from the different experiments and the atmospheric energy transport, we find that for the combined experiment, we find a southward movement of the ITCZ. And there is, for the combined experiment, we also find a northward energy transport. So basically, there is a northward energy transport with the combined experiment, which moves the band southward over the Indian Ocean. So, and looking into the strength of the Hadley cell, what we find is that there is a shift in the, we did both the zonal and the Indian Ocean region, because the southward shift happened over the Indian Ocean. So and also primarily because the aerosols are a regional forcing. So we have the impact of the aerosols are mostly seen regionally, it is very strong. So we averaged over the Indian Ocean sector, the Indian South Asian region and the Indian Ocean. And we find that there is significant strengthening of the Hadley cell over the Indian Ocean region. So over the Indian Ocean region here in the combined experiment as well as in the AER. So both the experiments, it is strengthening over the Indian region, the Hadley cell is strengthening. So how does it happen? So basically, when we see these are the radiation, so the top of the atmosphere radiation. So when we have aerosols, there is a large scale decrease in radiation. Basically, it reflects a lot of radiation. And this green curve is from the combined experiment. The blue curve is from the aerosol. So it sets up a very strong interhemispheric radiation gradient. This radiation gradient actually drives the southward shift of the convection over the Indian region. Now, looking into the spatial plot, so this is a comparison between the greenhouse gas and the aerosol experiment. So this side is the aerosol experiment and this is the GHG. Now look at the first plot is the precipitation. So when we have only aerosols in the system, the present aerosols compared to the pre-industrial, there is intense enhanced precipitation over this western Indian Ocean, especially towards the southern sector. And when we look into the upper tropospheric winds, we find there is cross-equatorial transport. So the anticyclone gets stronger, which helps in cross-equatorial transport of energy. And coming down to the surface, the SST gradients, the aerosols does not have much impact on the SST gradients. In contrast, when we go to the GHG simulations, we find that the Western Pacific precipitation, the Indo-Pacific region, there is high precipitation. And when we look into the upper level, we also find this upper level anticyclone over the Indo-Pacific region, it is strengthening. But most interestingly, for the GHG run, we have a very strong signature at the surface. So we have this warming over the Indo-Pacific region and less temperature. So we have a gradient of SSTs, and this is quite similar to the observed SST trend. So, and we have this intense lower level easterlies. We know in the recent years there has been studies which shows that the easterlies are increasing over this region. So now reconciling the model and the observed changes, we take the combined experiment because the combined experiment showed us that intensification and the southward shift. So when we look into the combined experiment, combined effect of the aerosols and GAG, it is not a non-linear, it's not a linear effect, it's a non-linear effect. And when we look into the rainfall, we see the southward shift in the ITCZ as well as the intensification of precipitation over Western Pacific. And we see this enhanced upper level anticyclonic circulation, 200 HPA winds, which basically transport energy northwards. And as a counterpart, when you look into the observed trends in the 200 HPA winds, you can see this intensification of this anticyclone over the region. Coming down to the surface, the model in the combined experiments very nicely shows the intensification of the easterlies and the SST gradients. And the observed trends in the SST gradients also shows the warming over this region and the equatorial easterlies, enhanced equatorial easterlies. So basically what we can say is, so the intensification of the Hadley cell that we see in the winter time over the Indian Ocean region is driven by the combined influence of both aerosols and GHG. Now, if we go into the future, what happens? So in one of our another study, what we tried to see is, we know that Europe is cleaning up, China is cleaning up, and India is also projected to clean up. So what happens when we take off aerosols from the system? So in the past, from now to 2050, these are for present 245 to the 2050. So we can see there will be large scale reduction over the entire northern mid-latitude regions. Only India is a region where we are increasing aerosols. So with respect to that, there is large scale input of energy over that region. So the shortwave energy over this entire extratropical region is increasing. So definitely this large scale input of energy in the extratropic region will drive changes in the tropical circulation and the tropical precipitation. So when we look into the precipitation, only from the aerosol removal, we find that all the global monsoon, northern hemispheric global monsoon regions shows intensification of precipitation. So the north, starting with the Northern American monsoon, the Sahel, that has got the strongest and most robust signal. We even have a strong signal over the South Asian region, East Asian region. So these are basically what is the change in the precipitation of the global monsoon regions. And this is driven by the lower level atmospheric moisture transport. So as the convection increases, the upper level transport, energy transport, southward energy transport increases, but in the lower level, we have large scale input of moisture from the winds into the convective regions. So here we looked into the atmospheric energy transport, moisture transport, and the Hadley cell, which is again deeply connected to the ITCZ. So we find that there is the southward energy transport, it increases, and the northward moisture transport increases. And this strengthens the Hadley cell. So because it is 2050 and because it's aerosols, we don't really see a movement in the ITCZ, but the strength is intensifying. And we can see that in the winds too. So the point that is here, going towards the future, we really don't know how we will change. There is a lot of uncertainty. So as it is, the models has a large bias. And then we have uncertainty from the forcings. So it will be very hard to tell how the ITCZ will move or how the organization within the ITCZ will change. So the key challenges in understanding the ITCZ is most of the models, majority of the models fail to simulate ITCZ properly. And we have this persistent biases in the model. We have the double ITCZ. We have the SST gradients in the equator are wrong in the models. The radiative feedbacks, the cloud convection schemes, they are not properly represented. So all this boils down to the changes in the organized systems, basically, over the equatorial region. So the cloud convection, so deep convection and mesoscale organization, that is a very big challenge in the models. We have this cold tongue, the upwelling, then the Bjerknes feedback, the wind circulation feedback is also not properly represented. Then another part is how do you attribute it, like what change comes from the anthropogenic forcing, what is from the internal variability of the system. For that, we need long records to or large ensemble simulations to identify, to decouple the anthropogenic forcing and the internal variability. And last point, but the most challenging point, is how the multi-scale interactions occur, how the mesoscale organizes to synoptic scale to thousands of kilometers rain bands. That is still one of the biggest challenges. So some recommendations, and there has been already studies on this, is the high resolution model, what we call the kilometer scale model. And these results are coming out, so which shows where we don't have convection is not parameterized. We have, it is like the systems are resolved. So, but that has to go a long way. Those models are not tested for the climate type of simulations. Coupling, improving the coupling processes is, we all know. And obviously, along with this comes observations and data integration, because as we go to the high resolution, we need this. And of course, we need to bridge the scales from meso to synoptic to large scale, and the extremes. That is most important. Thank you.
Thank you. Very nice. Thank you. Very nice overview. Challenges. So I'm wondering, so we saw in the previous talk that the rainfall is quite low, the snow bias. And I'm curious about what the reason is. And when you showed these maps, that it looks like the presentation can look all right.
The large scale patterns are all right, but when you compare the intensity, when you just compare it with observations, the particular amount of rainfall, that is not correct, because again, convection is still the major challenge in the models.
Yeah.
So, yeah, but the
do you think it's the
dry bias, yeah, definitely the convection. Like, we still don't know how to represent stratiform, like the observed stratiform that we have. The deep convection is overestimated. So that, and even the SST bias, like particularly for the Indian region, the equatorial SST bias, Indian Ocean SST, plays a bigger role in controlling what type of precipitation will happen. So that those things are still open. But the patterns and the transition, those are captured. The large scale signals, because it is driven by the teleconnections, it is driven by the energy, those we can capture. But
experiment, the stratospheric injection of the, but in the atmosphere really sustained for.
no, physically it's not. It is in the model. You can put aerosols there, and then you change the radiation, and then you see the effect. So it is modeling. In solar geoengineering, people are talking now. A lot of talk is there, but how much will happen?
It's indicating that in the stratosphere some pollution is there, aerosol is there.
Volcanic aerosols there.
That aerosol
No. This experiment was to see whether if you cool down, like if you change the albedo of the two hemisphere, how because ITCZ is a persistent problem, location of ITCZ. So they tried to just show that changing the albedo changes the position of the, so basically they corrected the African monsoon. That was the main idea of the paper.
So in the anthropogenic forcing that we talk about, the aerosols, anthropogenic aerosols are there only, right?
Yeah, natural and anthropogenic. So pre-industrial already has the natural.
But in the future, anthropogenic aerosols will reduce, right?
Yeah, only the anthropogenic.
Naturally, the natural aerosol will dominate.
The effect will be same, right? If you don't increase the natural aerosols, you can hear me? If you don't increase the natural aerosols, the impact will be same of the natural aerosols. You are just reducing. So if you compare weighted, yes, definitely the weighted change will be more from the natural, but the change is in the anthropogenic. We are not changing the natural.
Okay. Suppose we consider that the natural will dominate in the future because anthropogenic are reducing. So natural aerosols like from the Indian Ocean that the sea spray aerosols are there, and so because of that, it may give you the cooling effect.
See, no, for these experiments, these are modeling experiments. So the experiment's base state already has a natural aerosols. Okay, and it has got an anthropogenic. So we are changing the anthropogenic only. Until and unless you change this natural. So if you change the natural aerosols over the Indian Ocean region, then you will see an effect.
Yes.
Otherwise, you won't. But you will see if you change, if the aerosols over the Indian Ocean region changes in future, natural, then it will impact.
Yeah, that was my point actually.
Yeah.
In future, we change the natural, but in this experiment, the natural
Is fixed.
It is fixed. Only anthropogenic is changed.
But if you change, it will definitely have a bigger impact because we are reducing the anthropogenic. Yeah.
And so what I want to talk about now is go a bit more into the moist processes and talk about how the hydrological cycle is also a thermodynamic system. And embedded in this system, I mean, it connects to these heat engines. And so this is also then how I want to end is sort of, again, try to illustrate to you how one can link the processes that deal with evaporation and precipitation as they're related to heat engines, and ideally have some discussion about how this actually applies to the Indian monsoon. And I have some initial thoughts, but I'm sure you are probably more informed about this. But I want to first talk about, in general, the hydrological cycle. And so we saw the heat engines in the beginning, you know, that the surface heats, the atmosphere cools, and in between there's a heat engine that can operate. But we didn't talk about this partitioning between sensible and latent heat at the surface, this energy balance partitioning. And this is what we are going to also talk about now. And I want to actually start with the base state. So when we think about the hydrological cycle in a state of thermodynamic equilibrium, so where, you know, the cup of coffee is cold. Remember in the beginning we talked about hot cup of coffee in a cool room or cold coffee. A state of equilibrium is reached when air is saturated with water vapor. So this is Clausius-Clapeyron. And what this means is that macroscopically nothing happens. When you look at it microscopically, what happens is that the local rate of evaporation and the local rate of condensation are in balance. So just as many molecules go from liquid to vapor as there are molecules going from the vapor phase to the liquid phase. That's saturation. Why does it correspond to maximum entropy? Very good point. I mean, I think I took those slides out, but I can explain it anyway. It actually is, I mean, Clausius Clapeyron is actually derived from thermodynamics with the assumption of maximum entropy. And now, when you deal with a phase transition from, you have a warm water and warm water vapor, you deal with two types of energies that you distribute. On the one hand side, you have heat, sort of the thermal random motion. But in the liquid water, you also have that the water molecule, because of the dipole moment, they have water hydrogen bridges, right? And so there's binding energy involved. And so you would need some of the energy from the heat, from the random motion, to break up this binding energy. That means your thermal energy goes down. And when you reduce thermal energy, in principle, you would reduce your entropy, right? Because you have less, so it's like a minus delta Q, because you needed to spend some heat on breaking up the hydrogen bond to make it a vapor molecule. So that would reduce your entropy. But, but the water molecule in vapor state has more degrees of freedom to move around. So you have more states over which you can distribute energy, because it can also rotate, and the liquid water can't rotate. So it has a higher molar entropy, because it has more ways to move around. And so the state of equilibrium is the balancing of, do you increase the entropy because you have more thermal energy, or because you have more degrees of freedom over which you can distribute the energy? And now this sounds qualitative. What comes from this is what's called the Gibbs-Duhem relationship for phase transitions. And from this Gibbs-Duhem relationship, one can derive the Clapeyron equation. Then one uses the ideal gas law and comes to the Clausius-Clapeyron equation. So this is just to illustrate that you're probably all familiar with the Clausius-Clapeyron equation, but actually where it comes from is from thermodynamics, from maximum entropy, and it has also this microscopic component that the molar entropy of water vapor is higher than of liquid water, because the water vapor molecule is more agile. It has more modes over which you can distribute energy. Yeah? Yes? Yeah, absolutely. It's Le Chatelier's principle as well. Are you familiar with it? It's from sort of more from chemistry. Yeah, so actually we can talk about Le Chatelier's principle in a minute, because if you want to actually disturb this equilibrium, right? And it is being disturbed. This is the hydrological cycle. This is this picture here. It's sort of, I like, you can probably see, I like having pictures in my talks. This is here at the Danish, actually it's at the Danish border. This here is Germany, there's a ditch, and this is Denmark. And you have very dramatic, you have sunlight here and you have a thunderstorm cloud there. Yeah, so it's, for me, this is sort of my key picture for the hydrological cycle, because it has the energy input by the sun, heats the surface, and because it heats the surface, there comes Le Chatelier, right? So the phase transition of liquid water to vapor wants to counteract the heating. So it evaporates and takes up latent heat, right? It sort of takes some of the heat and puts it into breaking up hydrogen bonds. So the heating occurs at the warm place, where the evaporation takes place at the warm temperature. And the condensation, once you have motion in the atmosphere, and moisture can condense at one point in the atmosphere. And when it condenses, it again follows Le Chatelier's principle, because when it condenses, it releases heat. It sort of wants to undo that change again. And as we said, when you release heat, then air becomes buoyant and drives a moist heat engine. So in other words, you can generate motion from it, that I will talk about a bit later. Yeah. And so what we have is a hydrological cycle that is inherently in disequilibrium because your fluxes of evaporation and condensation are not locally balanced, but they're spatially and temporally separated. Yeah, and one reflection of this is that you have unsaturated air mostly. Yeah, and so now what I also find useful is to think of the hydrological cycle as not being something that is in steady state. So in other words, we have this imbalance between evaporation and precipitation, not just spatially, but also temporally. And then we can think of that we have actually one phase that is a precipitation phase where the air is dehumidified, creates disequilibrium in form of dehumidified air or unsaturated air. And then you have an evaporation phase that depletes this equilibrium. We talked about, when you evaporate water from the surface, right at the surface, your air is probably saturated, but then you mix it with unsaturated air. And just like when you mix hot and cold, also the mixing of saturated air with unsaturated air increases the entropy and brings the air closer back to equilibrium. So you have this one phase that, where by precipitation you have this generation of disequilibrium by dehumidification of the atmosphere, and then you have this depletion of disequilibrium by the humidification of the atmosphere during evaporation. And I was also thinking over the last days, when I learned about miso, that miso is more than Japanese soup, that's also monsoon intra-seasonal oscillations, right? Yeah, okay, I'm learning it. That maybe you can think of part of that oscillation being actually quite similar, right? You have a precipitation phase in your miso, and you have an evaporation phase in that miso. Yeah. Now, I want to look at both of these phases separately. So first look at how much actually evaporation is limited by thermodynamics. So we already saw the application of the maximum power limit so that the turbulent heat fluxes are driven by a heat engine, and because that heat engine transports heat from the surface into the atmosphere, your temperature difference gets depleted, so you have a maximum power state. But we didn't talk about this partitioning between sensible and latent heat. Now, I want to keep that, I also shortened this part here as well. So when you heat the surface, then the surface starts to heat the lower air. The air in contact with the surface. And what the sensible and latent heat flux do is they simultaneously heat and moisten the air. The heating causes buoyancy, and the moistening, the most you can moisten the air is keeping it saturated. Yeah, and the degree of so when you increase the temperature by delta T, the change in vapor pressure, saturation vapor pressure is given by Clausius Clapeyron. And from that, you can derive two partitioning ratios. This is what's expressed here, this gamma over S plus gamma and S over S plus gamma. Sometimes the S is also labeled the delta in the literature. This is the slope of the saturation vapor pressure curve. So that's Clausius Clapeyron. And gamma is the psychrometric constant. It deals with the specific heat capacity of the air. And so these two ratios, they add up to 1. And what you see here is that the warmer the temperature of the surface, so when this partitioning, the simultaneous heating and moistening of the atmosphere happens at a warmer temperature, then more goes into the latent heat and less goes into the sensible heat. And that's something, again, that one can actually understand quite easily, because the heat capacity of the air is fixed. It doesn't change with temperature. But to keep it moist, to keep it saturated when you heat it, you have that the Clausius-Clapeyron is basically an exponential function. So at a warmer temperature, when you increase it by delta T, you have a much greater increase in your saturation vapor pressure than when you are at a cold temperature. Yeah, and that's exactly what is being reflected here. So that's why at cold temperatures, most goes into heating the air, while at warm temperatures, most goes into moistening the air. And actually, just sort of on the side, I don't think I have that slide in here, but when you think about what happens to the global or what happens to the hydrological cycle with global warming, well, one thing is for sure: when you warm the surface, it means you enhance evaporation, and when you enhance evaporation, you strengthen the hydrological cycle, right? I mean, so and actually, when you calculate the relative sensitivity, you get these 2 to 3% that is known from climate models, that what happens with the hydrological cycle. Okay, and with this approach, we actually obtained this figure that I already showed on Monday. This is the measurements and the estimates for maximum power and this equilibrium partitioning for a tropical rainforest in Brazil, where you see that the evaporation follows this equilibrium partitioning very well, and the turbulent fluxes follow maximum power very well. Yeah, and so I think the utility of this equilibrium partitioning is really that you can check, for example, with climate model output, how far is the model from this equilibrium partitioning that gives you the local maximum rate of evaporation. Now, when we talk about the precipitation side, so I mean, here on the evaporation side, we get power from solar radiation. So some of that goes into evaporation, some of that goes into buoyancy and dry convection. On the other hand, when we have precipitation, we have the the water vapor condenses, releases heat. So we have a moist heat engine, and so you get buoyancy from this condensation. But in addition to generating updrafts, you also act to dehumidify the atmosphere, because when the rain is out of the atmosphere afterwards is drier. And so there you have some interesting dynamics. You have an interesting feedback that you don't have with evaporation. When evaporation takes place with a relatively fixed forcing by solar radiation, for the precipitation phase, the forcing is the water vapor, and the water vapor is movable. You can move it into as soon as you start motion. And so you can think of this as a positive feedback. So as soon as water vapor starts condensing, that releases, that causes heating. Heating generates power. Power generates motion. Motion causes the advection of more moisture, so you can actually enhance the condensational heating, which generates more power, and more power brings more water vapor, and so on. So you have a positive feedback that can self-accelerate. Eventually, of course, the atmosphere is dehumidified, so that reduces the water vapor and probably stops. But there are also, of course, other processes that happens. This is only picking two. But with these two, you can actually also show that there is a maximum. So when you start dehumidifying the atmosphere, in the beginning, you actually generate more motion. And the more you dehumidify, then more and more work goes into dehumidification. And here, so you have this maximum in generating motion and affecting moisture. And this is something that, again, one can derive from equations. We're still sort of fiddling with this description, yet Sarosh already moved ahead and tested sort of the outcome of that optimum, and looked at extreme rainfall events. So these are the 90% or above the 90% quantile, the reason why he looked at extreme events is because those are clearly convective in origin, and so they would relate to this heat engine picture. So here are observations from the CPC. Down here is a map of the estimate, and here is sort of a one-to-one comparison. Now it's not perfect, but I think for a relatively simple approach, it seems to capture the magnitude relatively well in this data set. And I think I already used this diagram in the beginning when I sort of motivated the use of thermodynamics. I mean, one thing I think what one can, when one uses this picture of a moist heat engine, I think it's very nice to convert this, or to expand the scale and not just look at convective rainfall events, but to actually look at the whole tropical circulation as a heat engine that is fueled by condensational heating. When you look at the typical rainfall rates of, say, 8 millimeters a day, and you convert this into heat release, then you have, it's about 30 watts per square meter per each millimeter per day of evaporation or precipitation. So you release about 240 watts per square meter of heat here, which is actually a lot when you think about it. As a reminder, the absorption of solar radiation is 165 watts per square meter at the surface. Yeah, so it's a lot of energy that is being released and causes updrafts, and then you have the descending motion in the subtropics, and that then actually generates disequilibrium in the hydrological cycle, because you have here a surplus, you have here more precipitation than you can potentially evaporate. In the subtropics, you have more evaporation you have more potential evaporation than what you can precipitate. Yeah, so you created hydrological disequilibrium in spatial form. Yeah. So we can also apply this picture to global warming. What would you expect? Well, we all know Clausius Clapeyron means that the atmosphere can store 7% more moisture per degree Kelvin. Yeah. Yep. I think you could call it relative humidity. Yeah. I mean, I think it's sort of integrated over the atmosphere, and then it becomes more complicated. It's not just relative humidity, because you sort of basically evaluate how far the water vapor content of the atmosphere is away from from saturation, right? Ideally, yes, right? And I mean, I think now where you ask, I mean, I think it's an interesting, different perspective, because when you look at metrics like CAPE and so on, you look like at LQ. Although the point is that you can't actually take all moisture out of the atmosphere, because that would require infinite work. Yeah, because to take moisture out of the atmosphere, you need to dehumidify, and that requires work. Yeah, and so instead of looking at how much can you take out, I think the better way to look at it is, this is saturation, and how much can you take out and get away from saturation? Yeah. So saturation is easy. Unsaturation or unsaturated air is not so easy. Yeah. So back to climate change. So with each degree warming, 7% more moisture. So in other words, we amplify this whole range of equilibrium to disequilibrium, because you have basically a greater variation between saturation and unsaturation. Now, when you have more moisture in the atmosphere, your heat engine becomes more powerful. So it can perform more work. It can simultaneously dehumidify more, and it can accelerate more, right? And because it can dehumidify more, this is why this line shifts here to, this shifts the disequilibrium higher up. but it also accelerates more, and so these dynamics actually take place in shorter time. And this is something that is already known, that especially in the extreme rainfall events, that they become shorter. Yeah, that there's a shortening of extreme rainfall. So in other words, what we can already infer from this is that we get shorter and more intense rainfall events, and this increases the likelihood of more floods. And in the evaporation phase, well, we saw that we have change in the equilibrium partitioning, but that's only 2 to 3% per Kelvin. So in other words, that means that there will be more potential evaporation. And I refer to potential evaporation because it depends on water availability on land, for instance. So evaporation will tend to increase, but not as much as precipitation increase. And so that means that the time until we get another precipitation event actually increases. So we have longer and more intense evaporation periods, and that would relate to more droughts. And so I think I hope what I can illustrate with this picture is that one can argue for this actually just with a little bit of physics and the thermodynamics. And there might be all kinds of variants that modify this picture, but I think overall, I think it's a nice picture that one can grab and sort of understand and say, okay, this is likely what's happening. And if you want to put it in one phrase, I would say, well, I think one could say the hydrological cycle becomes more extreme. You know, you have more variations in the precipitation and in the evaporation phase. One can also understand the wet gets wetter and the dry gets drier hypothesis from Held and Soden, because when you have 7% more water vapor in the atmosphere, your tropical circulation should actually increase. And I just want to sort of point out, I mean, so before lunch, we saw the talk about the ITCZ and that climate models typically show a decrease in the Hadley circulation, if I recall that correctly. But on Monday, Krishnan was also saying that he actually, in that new model that they used, where they actually see an increase in the tropical circulation, and that observations also seem to indicate that. And I think here again, sort of when you think of the tropical circulation as being the result of a heat engine that's driven by condensational heating, it sort of becomes almost straightforward to think, well, the humid regions become more humid, the circulation becomes more intense, and the subtropical regions become drier. And so the wet gets wetter, the dry gets drier, right? So that's consistent with the picture of Held and Soden. Now, how this all relates to the Indian monsoon, I only have one slide, and it's my last one, because I'm really curious. So, I mean, I think I had some ideas. So this is sort of what I came up. Again, relating it to MISU, right? I mean, so when you have periods of evaporation and precipitation, you have like oscillations between the dominance of dry heat engines and moist heat engines. And the difference is that the moist heat engines, because they're driven by moisture and they can structure the flow because they can concentrate the moisture, make it more powerful. They can sort of contribute to the circulation and also across scales. And I think this sort of relates to this interaction of scales. So, I mean, I think these are just some thoughts, but I think that could be helpful to look at or to think of these oscillations as being this kind of interplay. The other part that I wanted to, I mean, that there are certainly differences in energy balance partitioning between these two for these engines. And last but not least, this is actually less about the moist heat engine, but more about the discussion we had yesterday with one group. We're dealing with precipitation chain or anomalies and evaporation anomalies. And about that, I think, what was it? The model showed that in the humid areas, you had with an increase of precipitation, also an increase in evaporation instead of a decrease in evaporation. And yeah, I mean, if you want to talk about that, I mean, I think we discussed that last night and came up with what the results or what the explanation could be. Yeah, and I think with this, I mean, again, I mean, as you can see, it's not much on the Indian monsoon. Maybe you hope for more, and I also hope for more. And so maybe over the next year or so, this can become more concrete in the discussions if you are interested. And so with this, I'm at the end of this talk. And maybe one slide. In case of you go to the EGU, I'll be also at EGU the whole week. And you can meet us there. Actually, Tejasvi and Saurabh are also going to be there. I'm also going to be there, for example, Thursday. I'm actually involved in this journal from EGU. It's called Earth System Dynamics. I mean, there's a lot of output from PIC and Hadley Center and so on. So that's a little bit of advertisement. And if you are interested or want to know about publications, you're also free to just contact me. But with this, okay, I finished it. Yeah.
It means many things we know, but we have learned how to look it in a different way. I have a question. I will ask that first.
Yeah, and I think absolutely. I mean, to me, it has also been quite a different way, and I think in the end, it's not inconsistent. Yeah, but it can also inform.
Thanks for the talk. And so when it comes to the accelerating hydrological cycle, I agree on the local, spatial, and temporal scales, but there are new theories that says the latent heat, the large scale is not really driving the Hadley kind of circulation. So people say that the deep convection has the latent heat release, and that is balanced mostly by vertical motion. So in the thermodynamic equation, these two terms balance nearly each other. What happens is, the deep convection happens, there are gravity waves generated through the pre-troposphere. They kind of remove the temperature perturbations, and the gradient in the pre-troposphere is not that. So the temperature gradient approximation. In that scale, I'm not sure whether the latent heat is still considered to be driver of the planetary scale circulation. There are other frameworks coming up.
Okay.
Explain that the residual adiabatic heating or whatever is left after that balance is so small that it is calculated to drive the large scale kinetic motion.
No, but I'm interested to learn more about it.
It's a weak temperature gradient approximation. People are working on it.
Okay.
Adams from Wisconsin, Madison. That's quite kind of theory in the tropical region.
Okay.
But I do agree with the cycle happening, the feedback between the heating and the circulation at local temporal spatial scale, but not sure that scale.
Okay. Yep. Yeah, thank you. Well, maybe I can also just add, when I think, we also saw this morning about how the ITCZ moves on land, it moves, but over the ocean, it doesn't, right? And I think that has just, I think one can think about this, when you're over the ocean and the ocean temperatures hardly react to the seasonal cycle, right? I mean, the temperature variations are minute. And it's the water vapor that drives the circulation, then there's no need for the Hadley cell to move, right? Because it just is driven by water vapor input, and it, however the Hadley cell organizes is the way it organizes. Once you're over land, land, there you have this difference that the land doesn't buffer the solar radiation, but it heats the surface directly. So it drives a heat engine, the dry heat engine, pulls the moisture from the sea on land, and that somehow interacts to push or to pull the ITCZ on land, right? Would you agree to that picture? Yeah, I mean, there was something that actually I talked to Akshaya Nimbuk, I think is her name, from IIT Bombay last year, and we thought that was actually quite cool. I mean, I always think that something is cool when I feel like I learned something, and that was sort of one of those moments where I thought, yeah, never thought about it. I mean, I think the typical explanation is, the Hadley cell follows solar radiation, but the solar radiation is not the direct driver, right? It's the water vapor. Of course, solar radiation evaporates, and so it drives the generation of water vapor. But then the Hadley cell can organize itself however it wants to, condense the water vapor. Yeah.
Atmospheric science, say that is saturated adiabatic process, pseudo adiabatic. It's just like that. There is a moist air person from the surface. It is rising
Mm-hmm.
at some level. Moisture gets condensed, and as you have very right, that condensational heating takes place, and after that again it rises.
Yep.
That rising, now I am trying to just match that rising. What that rising, whatever energy is required, is it that condensation?
I mean, I actually had
After that it becomes dry actually.
Eventually becomes dry. Yeah. And, I mean, I had a discussion with Carrie Emanuel about this actually, because when you are inside the cloud, you can derive, or inside the cloud, there is an equilibrium between the vapor phase and the and the water droplets. Yeah. So it is in thermodynamic equilibrium. But the disequilibrium is actually between the updraft and the downdraft, right? So I think that relates to your comment that I mean, you have some pseudo adiabatic, moist adiabatic profiles inside the cloud, but then you have the dry adiabatic next to the cloud.
After that actually become dry.
Yeah.
After that it became dry. Because when we are finding out the equivalent potential temperature, we follow this one. We take one moist air person, allow to rise.
Yes.
Allow to condense at some level. Mm-hmm. Allow again
to rise
until it becomes completely dry. Then
it sinks.
Pull it.
Yeah, but although I think at the clouds that there are sort of outflows all the way on the way up, and then you have the re-evaporation of cloud droplets and so on, and so, but you have a sort of the air that rises cools less strongly than the air that sinks, right? And that's creating temperature difference.
Of your this thing, I was just trying to match. It may be also an example of moist engine.
Yeah, absolutely. Yeah.
I was just wondering whether you have to explain like. Thank you very much.
Yeah. So, sure.
Question. So thank you very much.
Yep.
Professor Alex. Very nice lecture. We all have been very much learned, and we have learned many known things in a different angle. So,
good. Yeah, and I thank you for I mean, especially last yesterday afternoon we had some very stimulating discussions. It was very, very nice. Yeah, maybe we just maybe we continue. I mean,
you continue after that only. So now we will have the talk by.
I'd like to update.
Okay. Hello at Planck Institute, and we will talk on sensitivity of hydrological cycle and precipitation extremes to global warming. Thank you.
Thank you. Hello, everyone. I've changed my title a bit because I wanted to specifically talk about insensitivity of water cycle. I wanted to specifically talk about drying trends of land and the atmosphere. There are lots of things you can talk about when you talk about broadly sensitivity of water cycle. So, first thing that I want to start with is that I think a lot of things that I will say in the beginning would be some repetitions, which you would have heard from Axel, but it would be good that we have those concepts at hand. So first thing that we need to acknowledge is that water cycle is closely tied to Earth's surface energy balance. Its reason for existence is that there is a residual heat at the Earth's surface which needs to be transported, and water cycle serves as one of the mechanisms which Earth's surface has to send its heat into the atmosphere and then cool the surface down. So if you see solar radiation on an average is around 165 watts that gets absorbed in the Earth's energy balance. And it is worth noting that latent heat flux, which Earth sends into the atmosphere as evaporation, is almost half of it. So half of the heating that gets absorbed at the Earth's surface goes actually into the evaporation process. So so that is what feeds the Earth's water cycle. And it is often useful to look at Earth's water cycle, especially the atmospheric branch, using a bucket model. So you can imagine atmosphere as a small bucket, which is continuously transporting water. The bucket is really small, but it transports water constantly. Evaporation is what fills the bucket, and precipitation is a process that drains the bucket. And Axel also gave this analogy very nicely in his talk, that how there is a dehumidification process which has its own time scale, and then humidification process which is slower. And what I now want to talk about is that when we talk about sensitivity of water cycle, or before we start talking about drying trends, something like drying trends, there are two key things we need to acknowledge. First is that this bucket size of the atmosphere is determined by the temperature of the atmosphere. So Clausius-Clapeyron relationship, which is very well known, we have been talking about it a lot. So the water holding capacity of the air increases exponentially with the temperature. Warmer regions of the earth, or warmer portions of the atmosphere, Earth's atmosphere will have the capacity to hold much more water than the colder regions. So the bucket size is determined by the temperature of the atmosphere. So that was one component in the previous figure. So there was a bucket which was whose size now we know is determined by the temperature. Now again there was a humidification process, that the process that fills the bucket. What determines that process, that also I think Axel covered in his talk. It is determined by something called equilibrium partitioning. So the residual energy at the Earth's surface, the surface energy in the surface energy balance, whatever net radiation remains at the Earth's surface, needs to be converted into sensible and latent heat flux, and it can either go into humidification of the air, which is the blue line that you see, or it can go into the blue line is the humidification or moistening of the air, or you can provide the air with sensible heat flux so that it stays buoyant. That's essentially the idea behind the equilibrium partitioning, and this forms the basis of the flux that fills the bucket. So essentially there are two different processes or two different concepts which are at hand. The bucket size is determined by directly the Clausius-Clapeyron relationship, and the flux that fills the bucket is determined by equilibrium partitioning. And this factor S upon S plus gamma multiplied by net radiation is the evaporation that you can get out of net radiation by equilibrium partitioning. So when you think of sensitivity of water cycle or how things will change, the bucket size or the water holding will scale using Clausius-Clapeyron equation directly. But for evaporation to scale, or whatever sensitivity you want to derive, it will come from this factor, which uses Clausius-Clapeyron but is slightly different than that. These are the two things which I wanted to mention first. So here in the atmosphere, the bucket size is determined by Clausius-Clapeyron. So whenever we'll talk about dryness there, this is what will be important. And for evaporation, there's a slightly different process that it decides the sensitivity. And so when we talk about dryness, there are actually two ways you can essentially look at whether or not in the water cycle things are getting dry or not. One is in atmospheric perspective. An atmospheric science, or a person who looks into the atmosphere only would look at vapor pressure deficit or relative humidity to determine how dry the atmosphere is or how dry one component of water cycle is. There is another way to look at dryness, is a hydrologic way, where you would look at the aridity of a region. And here you would use, so the one component atmospheric branch uses just the bucket size. And this second perspective of whether or not there is drying or how dry the region is, uses something called potential evaporation and precipitation, the balance between potential evaporation and precipitation. And a balance of these two determines characteristic properties of different regions, but they are not very different from one another. So you would see that atmosphere is super dry in regions which are hyperarid. Okay, so so in order to systematically examine these two visualizations of dryness, and then at least approach whether or not hydrological site or regions are getting drier, what we need to acknowledge is that there are two unique roles land plays in the Earth system. There are essentially multiple others, but for this understanding, what we need is that we need to understand these two roles. First is that land can dry out. Land can be wet or land can be dry. This is slightly different than the oceans because ocean surfaces will always be wet. Land can dry out, which can change something. And second is how land deals with surface energy balance, which is different than the oceans. So land is forced to put residual heat above it in the boundary layer, whereas oceans can absorb that heat in itself. So these are the two properties which actually differentiate land and lead to two different ways of approaching dryness that I will explain in a bit. So if you, so when over a cycle, over a course of a day, we have from sunrise to sunset, shortwave radiation heats the Earth's surface, which puts some residual heat inland. However, the cooling processes can happen day and night. The radiative cooling from land can happen day and night. So essentially what happens is that there are components which heat the Earth's surface, Earth's shortwave radiation, and there are components which cool the Earth's surface, which essentially forms the Earth's energy balance. So we have shortwave radiation which asymmetrically heats the Earth's surface only for a part of the day, and this component here cools the Earth's surface day and night. And we have additionally this component here, which is called together turbulent fluxes, which only operate during the day, and they also cool the Earth's surface.
via two components. One is the latent heat flux and the sensible heat flux, like I talked about. However, what happens is that these two components here, net long wave radiation and sensible heat flux, while they cool the Earth's surface, they actually heat the Earth's atmosphere. Latent heat flux does not do that, because the energy which we put into latent heat flux goes into the phase transition. That's why it's called latent heat. And since these two components heat the Earth's atmosphere, what we have is that solar radiation, as it progresses, leads to heating of the Earth's atmosphere, lower atmosphere, and we get something called diurnal temperature range. So T max minus T min happens because these two components are actually putting heat from Earth's surface, residual heat from Earth's surface, into the atmosphere. And why am I suddenly talking before talking about dryness? Why am I talking about all this? I'll come to that in a bit. But what you can now infer is that on a day when you have more solar radiation, essentially less clouds, you will get more heating of the lower boundary layer, and you will get more diurnal temperature range. So maximum temperatures will be high on a clear sky day. That's what you can essentially infer from this. And you can see this clearly in the observations. This is from a study by Sarosh, where he showed that as clear sky fraction increases, as you have more clear sky days, the diurnal temperature range is significantly higher in the observations. Now, why all this matters for our hydrologic sensitivities or the way we perceive dryness is because there are two ways to dry the atmosphere. One is you increase the bucket size. So essentially vapor pressure deficit, whenever you try to compute, or relative humidity, whatever you feel comfortable with, will involve either saturation vapor pressure and actual vapor pressure. And this here is a direct function of temperature, like we discussed. So if you heat the lower atmosphere, you're essentially you're essentially creating the stronger bucket size. So you will dry the atmosphere not because you're taking moisture out of it, you leave the moisture untouched, but you dry the atmosphere by heating it because you increase the bucket size. So that's one way of drying the Earth's atmosphere. And so this can be quantified if we understand this, that this quantity here, the actual vapor pressure, does not vary much at sub-daily scale. Since Earth's water cycle has a residence time of 10 days, so this takes longer to respond for any process or any evaporative process. So this here, when you see in the data sets, will not vary much in sub-daily time scale. Essentially, any variation in vapor pressure deficit, most of the variation in vapor pressure deficit from one day to another would be because saturation vapor pressure changes over a course of the day. And this can very well be quantified if we just take a Taylor expansion of it and just take the first term from it as a first order approximation. So slope of saturation vapor pressure curve times the temperature difference can give us the change in vapor pressure deficit. So now our systems understanding reaches a level that we started with heat storage in the lower atmosphere intuitively, and we have now understood that solar radiation can cause heating of the lower atmosphere, and that heating can cause drying, not because we take the moisture out, but because we increase the bucket size. And essentially, diurnal temperature range, which came out of heating because of these two heating terms, also causes the drying of the atmosphere, the vapor pressure deficit in the atmosphere over the course of the day. And consequently, on a clear sky day, you will get more diurnal temperature range and more vapor pressure deficit. So, so this here, I'll stop. I'll partly arrive at what we have is that now we have a systems view of how vapor pressure deficit or relative humidity in the atmosphere comes about. It is closely tied to Earth's energy balance and how it is putting heat in the atmosphere. What is the nature of the heat being put? If the components are what heats the lower boundary layer, you will get a stronger drying of the atmosphere. However, if you have latent heat flux, higher latent heat flux, that won't contribute to the drying of the atmosphere. Now, what we have is that we actually have estimates or theory available to quantify each of these steps that I just showed you. There is an estimate of diurnal temperature range now analytically available. This was done by Sarosh from our group. What we can show is that if we assume linear boundary layer growth, then essentially this relationship already exists. It is well known that assuming linear boundary layer growth, then this expression equates to the heat that you store in the boundary layer over a course of the day, maximum heat storage. However, we can now compute that heat by integrating non-latent heat input into the atmosphere from surface energy balance. Like I showed you, this is the term which doesn't take part in making the diurnal temperature range out of the shortwave radiation of the sun. So we subtract it, and if we integrate it throughout the day, we can estimate DTR from this relationship. So what we can do is that if we can have an analytical expression for this latent heat flux using the heat engine view of the Earth's atmosphere, which Excel has been describing in past 2-3 days. And what we can get is that from this, we have a hot reservoir and a cold reservoir and a heat engine operating between the two. So Earth's surface has two competing ways of cooling itself. So one is it can cool it radiatively, or it can use the turbulent heat fluxes, sensible and latent heat flux to cool itself. And what we can get is that if we maximize the power here, we can get an expression of turbulent heat fluxes, sensible plus latent heat, which actually matches very well with the observations. So we can use this little theory here, and we can then do equilibrium partitioning. So that's why I revised those concepts here. So this here is a measure of how much sensible and latent heat flux together do we have from the heat engine. We can then perform equilibrium partitioning on it and multiply it with that dryness factor, and we can essentially have a analytical solution for it, which would look something like this. And what we have is that we have now a analytical expression for diurnal temperature range, which takes into account the radiative forcing of the Earth's surface, but also takes into account the surface properties, for example, dryness. And this actually works really well from observations. This here is from FluxNet. I would say reasonably well. There are still huge errors that we need to address in the future, but more or less the signal is captured really well. This is in ERA 5. This is in FluxNet. Now, the next step is to go from diurnal temperature range to vapor pressure deficit. Like I said, that it all starts from Clausius-Clapeyron equation or the slope saturation vapor pressure curve. What we can do is we can do a Taylor expansion around it, and then essentially write vapor pressure deficit as slope of saturation vapor pressure curve minus the temperature difference. If we take those temperature differences as maximum temperature and dew point, we can get maximum vapor pressure deficit in the day. And I've added a small little approximation here that let's assume T min is always equal to dew point, which if you look at the data sets works reasonably well. Almost more than 75% of the Earth's observations generally follow this. So then you can write vapor pressure deficit as slope of saturation vapor pressure curve times diurnal temperature range, which actually works very well. This is observed from FluxNet, and y-axis is the estimate, and you see it for two types of regions. One are dry, one are wet. So what we have is that we can now estimate dryness of the atmosphere, the atmospheric branch that I showed you of estimating dryness, very well using first principles and thermodynamics. What we can now talk about is that what can we infer about the hydrologic perspective of dryness, this aridity index. So essentially, you would see a lot of literature in past decade coming out arguing that most of land regions are getting dry, or drylands are expanding, or dry regions are strongly drying because they use some metric of potential evaporation. And essentially the argument is that in dry regions, potential evaporation increases much more than precipitation. Precipitation cannot catch up in a warmer world. And essentially you will become, the land regions will become drier. But what I would like to point to is that often the estimate of potential evaporation that we generally use, which is considered mostly robust, is Penman-Monteith equation, which essentially has two parts. One is the net radiation of the Earth's surface is being partitioned into evaporation, and then another part which uses vapor pressure deficit. So essentially atmospheric dryness, when we estimate it, it goes in as a forcing, and it uses atmospheric dryness as a driver of evaporation rates to estimate an aerodynamic component of evaporation. Those two added up give you a potential evaporation estimate. While we have this, which is nice theory for potential evaporation consistent with the considered more robust, what we also need to acknowledge that any estimate of evaporation that we generate. Potential evaporation means how much water can we evaporate given no constraint on water supply on the Earth's surface. Any estimate that we get should follow Earth's energy balance, because evaporation in the end is a phase transition process and its role is to satisfy surface energy balance. So whatever estimate you get out of the equation, you should at the end of the day have enough energy available for at the Earth's surface to supply to latent heat flux, that amount. Yes. Yes. Yeah, they are. I mean, they're actually same. It's just that when the theory developed, they wanted to include plant transpiration as well in it. So then you have terms like, if it's defined for a cropland, these parameters these parameters vary based on what kind of surface that you have. If it's plants, you can have a separate surface resistance to it from leaf, and then you can have an aerodynamic conductance as well. So those things changes, and based on that, definitions changes. For example, you can call it reference evapotranspiration based on how you estimate these coefficients. But the idea is essentially the same, that you don't have enough water, no water stress. How much water would you evaporate? So what I was saying is that it should be consistent with Earth's energy balance. But when we test it on era 5, for example, on x-axis, it's the net radiation from era 5 reanalysis. And on y-axis, it's the estimate from this equation using FAO's parameterization, essentially the reference evapotranspiration. And each point here is a grid cell on Earth on land regions, long-term average potential evaporation from that region, and color represents aridity index of that region. So red ones are hyper arid regions of the Earth. Sahel would be somewhere here, and Thar Desert also would be somewhere here. And these are the blue ones are the humid regions of the Earth. So Amazon rainforest and Northeast India, regions like that would be somewhere here. And this here is y is equal to x line. So essentially what happens is that a lot of arid regions estimate of potential evaporation, how much water we can maximally evaporate, is more than 5 times or up to 5 times the energy available in those regions to put into sensible and latent heat fluxes. This is what you would partition into sensible and latent heat flux. This is what you would need to perform to evaporate the amount of water. So something is going wrong in the equation in arid regions, because it generates strong evaporation rates which seem to be not consistent with Earth's energy balance. And when we look at the two components of this equation independently, for example, this here is the radiative component individually plotted, and this is here is the aerodynamic component. The violation comes only in the aerodynamic component. Radiative component is more or less consistent, which is obviously the case because you partition net radiation itself. And this component here uses dryness of the atmosphere to drive evaporation rates. And so essentially something goes wrong in this component. And so we'll continue our little intuitive diagram to understand this. But what we have is, if you see that most dry regions have very high VPD and very high diurnal temperature range also. So this essentially links to our story that I began to reach the atmospheric dryness estimates, that this has to somehow to do with how we were putting heat into the lower atmosphere. And this again is the estimate that I did from FluxNet sites. On x-axis, you see wetness of soil. And if you see that as we have dry and dry soil, both diurnal temperature range and vapor pressure deficit increase significantly. And this is what we estimate from our analytical approach. So DTR is estimated, the orange ones are estimated, gray ones are from the FluxNet. And again, VPD is gray one is from the FluxNet, and orange ones are the estimates. So theory captures it very well, but it increases significantly along the dryness. And that's what I wanted to explain to you, that something happens in this picture when there is water stress. What we had so far understood is that more solar radiation would lead to more heating, which would lead to more drying, and then eventually more, basically DTR can lead to more vapor pressure deficit. But when there is water stress, even though nothing changes in the radiative forcing, dryness leads to more H. So dry surfaces are forced to partition more to sensible heat flux, which essentially causes even more heating of the lower atmosphere and even more drying of the lower atmosphere, even though nothing changes in the radiative forcing. So what we then have is that if we consider systems view of vapor pressure deficit, we can now arrive at systems view of the Penman-Monteith equation, essentially to understand potential evaporation. From solar radiation, we can get variations in temperature, basically the diurnal temperature range, which gives us vapor pressure deficit. And while computing potential evaporation, we use this diagnostically, we would either observe this or we pick it from a model over a dry region or a wet region, we put it in an equation and we get an estimate for potential evaporation. But when there is water stress, this is inflated, not because solar radiation changes, but because there is water stress. Then you get stronger vapor pressure deficit simply because surface was dry, not because radiative forcing was high. And you would use this extra vapor pressure deficit as well, because this is a part of the observations, and it will give you unnecessarily estimates of potential evaporation. Note that potential evaporation is defined only for a wet surface. You are defining that hypothetically, if surface was wet, what would the evaporation be? And hence, this vapor pressure deficit here, which came because of surface dryness, should actually not go into the equation. That's what we argued. And in order to estimate this vapor pressure deficit, which is free from water stress, we can combine the whole picture that we have. So in the diurnal temperature range theory, we have surface dryness as a factor going in our analytical formulation. And then we can estimate that water stress free diurnal temperature range from this model now, and use the relationship VPD is equal to S time DTR to get a new vapor pressure deficit, which is free from surface dryness. And we put that VPD in this equation. And what happens is that the curve, which was showing strong bias in the beginning in the RF5, starts to converge towards surface energy balance. All the arid regions start to actually approach y is equal to x line if you start removing imprints of dryness from vapor pressure deficit. So what we have is that we have what I discussed is that there are two views of viewing whether or not parts of water cycle are getting dry. So one is atmospheric view, where we have an estimate VPD is equal to S time DTR. And then there is a hydrologic perspective to dryness, which uses potential evaporation, but atmosphere generally goes in as a forcing. But what I showed is that this forcing is not just radiative, it also responds to dryness of the Earth's surface, and hence a part of it should be removed. Now, we should also talk about what can we infer about trends. So far what we have been talking about is mean potential evaporation rates, mean vapor pressure deficit estimates. What we can also infer from this is that, so first part, the atmospheric branch, we can actually use this theory to attribute where the trends in vapor pressure deficit or dryness of the atmosphere are actually coming from. So we can decompose this into trends that come from thermodynamics, basically Clausius-Clapeyron equation, trends that actually come from diurnal temperature range. And if we actually not use the approximation that I told you in the beginning of T min is equal to T du, we have one more small factor that goes in. Trends may come from that as well. But what we have is that this decomposition actually works really well. And theoretically, what the estimates say is that this scales at 7%. Clausius-Clapeyron equation scales at 7% per Kelvin. And diurnal temperature range has been argued to reduce by 2% per unit change in global warming. And what I found is that there is no theoretical estimate for this quantity, but it varies spatially. It leads to spatial variation on Earth, but it varies. It is much less than scaling of diurnal temperature range. It stays between -2 and 2. And so this is the normalized trend in VPD. So all trend in vapor pressure deficit or relative humidity. I'm not showing figures for relative humidity, but this whole theory can essentially be translated to explaining trends in relative humidity as well. So all these three components actually add up to trends of vapor pressure deficit. And what we find is that it is the Clausius-Clapeyron equation which is actually driving trends globally. The first component, which comes from slope of saturation vapor pressure curve, is the dominant driver of trends. However, there is some spatial distribution which comes from this third component here, which has to do with how dew point changes with global warming, or basically actual vapor pressure, it varies with global warming. And if you see, India is an anomaly here. It appears that the trend is decreasing in India, which is not because of this component, partly because of this component, but quite strongly because of this third component, which has to do with the dew point temperature. And this is how we can decompose where the dryness trends of atmosphere come from. And coming to the trends in the hydrologic branch, so we can also have trends in potential evaporation that were used previously to argue whether or not land regions are getting dry, or how basically there is this hypothesis of global aridification, that on an average all land regions across the globe will get drier with global warming because hydrologic cycle intensifies and potential evaporation increases a lot. But what we find is that after you apply this correction, this black line here is the trend in potential evaporation on an averaged over all land regions of Earth before you correct, and after correcting, the trend reduces by 50%. So a lot of trend that you see in potential evaporation is actually coming from the fact that surface is dry, and on a dry surface, VPD increases much more. And that trend is because of dryness of the Earth's surface. So essentially, that should not be a part of potential evaporation, which should be water stress free. And after this correction, what we also find, which was counterintuitive, is that the dominant drying regions flip in the over the Earth. So earlier, the understanding was that arid regions are the ones which are drying much faster than the humid regions. The black ones are the trends which without correcting. So arid regions, if you see, have a stronger trend than the humid regions. However, when you correct for the surface water stress in the hydrologic dryness estimates, the trends in arid region almost vanish. They are very small. What the strongest trend which remain are in the humid regions. So the counterintuitive argument here is that humid regions are the ones which are drying more than the arid regions, because potential evaporation is increasing much more there. And essentially, when we come back to scaling, the other estimates of potential evaporation, they exist. For example, there is this Priestley-Taylor method and equilibrium partitioning, which Axel also discussed in this previous lecture. They all give scaling of around 3.2% or around 3% per Kelvin. And Penman-Monteith earlier used to give scaling of up to 5 or 6%. But what we, after this correction, actually this number, I didn't write it here, it actually converges to close to 3% again. So which becomes consistent. So you could ask that, so what do we infer out of all this? And like I said, that this is a figure from IPCC, and these purple regions that you see are where IPCC argues that there is a high confidence of increase in dryness, which are essentially the arid regions of the Earth, and there are partly humid regions. But IPCC reports, whatever they use, the estimates generally come from potential evaporation estimated using Penman-Monteith equation or some variant of it. I tested it on around 3 or 4 variants, from FAO to other variants by which came recently, which claim to be consistent. For example, there are variants which actually incorporate CO2 fertilization effects, but they still also have this bias. But when we address this bias, this representation from IPCC can even change, that what regions of the globe may aridify with global warming. And so essentially, the summary is that there is an atmospheric view of dryness, and then there's a hydrologic view of dryness. And the atmospheric one is actually generally used to infer the hydrologic drying trends, but it is not generally independent of dryness of the Earth's surface or purely radiatively forced. We need to first derive just the radiative component out of it and to feed into the hydrologic trends. So yeah, to summarize, so I discussed 2 pathways or 2 ways to quantify dryness, and I showed you analytical ways to estimate those 2 components. And then in the hydrologic one, I showed you that there is there's a bias in the Penman-Monteith equation, which we gave an analytical correction for. Thank you. I'm really happy to take questions.
I'm just looking into radiation topic, how it will change.
Wait a second. I think actually nothing changes in the radiative budget. All we do is that radiative budget is here, R in. It stays the same. We don't alter it. From it, something gets subtracted, which is the latent heat flux, which was to be modeled. And we had surface dryness factor as which goes into the theory, and rest of it is expression for equilibrium latent heat flux, which comes from the heat engine. And then nothing changes in R in. it stays the same. We just switch off this dryness factor. So wherever the dryness factor is super high in arid regions, its value would be 0.1, 0.2, something like that. We just turn it off and then let it remain at the thermodynamic equilibrium latent heat flux. Okay. I mean, yeah, that's interesting, but I have not actually plotted it. It would be good. But what I found is that some arid regions where IPCC stays unconclusive, these would stay as is, that there is no strong signal of drying. But this region, for example, here will go away, and this region here will stay as a drying region. I see. Okay. Okay. Yeah. Yeah. So in future, yeah, I mean, I understand. I think your point now. It's just that I think that would be the next step, which I have not done yet, to examine that in future. Basically, how would aridity pan out? So right now, it would be like a hindcast analysis that previous trends are reproduced very well, versus I would say that next step would be that modified potential evaporation equation. Does it give me a better water balance estimates or something like that? Then if I can use it to infer drying trends, then I think I would be able to argue about it. Yeah.
Temperature has the difference between max minus T. Now, you are mentioning in your talk about the increase of DTR. Increase of DTR. Now, DTR can be increased by two ways. One is definitely by increase of maximum temperature. But another one way is also there. That is by increasing the. Generally, I the main equation or temperature change. They are actually what happens. That is, temperature increase can be done if there is warm air coming from some other region. Second thing is, of course, your diabaticity, radiativity, what you are telling. Another one thing is also there that if the atmosphere is stable and if there is clear sky, anticyclone is there. In that case, sinking motion undergoes adiabatic compression, and that adiabatic compression also adapts with the radiative. As a result of which, I think this time itself, what happened? Even in Pune also it face. Daytime temperature is very high, and night time and early morning temperature is very less, and as a result of which TTR is very high. In presence of some anticyclone, when there is an anticyclone is there, okay, then in that case there is sinking motion, and if the atmosphere is stable.
Yeah, then you will get a higher Tmax, something like that. Yes.
So therefore, for DTR mechanism, what I mean to say, for DTR increasing mechanisms may be many actually. One may be, of course, as you have very rightly told, that is radiative solar insolation. Also.
Yes.
That we call it as a diabetic heating. Actually.
Yes.
Diabetic
Yes.
heating. Besides that, also this two.
Yeah. I mean, I think, yeah, I understand this. Yeah. Thank you.
And thank you very much to the entire MPI team for the very nice lectures. And really, from your lectures, actually, we have really seen that how the known things can be looked in a different way. Completely thermodynamic period. Very much thankful to all of you. So now director could not come. On behalf of director, I wish to express my sincere thanks to entire NT-ATW and there, Mr. Dr. Vijayan also for conducting such a nice lectures. Thank you.
Thank you.
Thanks to all the audience.
We have earned.
We have learned. Yes. So हो गया हाँ
Yes.
हो गया तो बताओ
Yes, sir. Yes.